Hello there, and welcome to Science for Sleep, where curiosity slows down, explanations take their time, and the universe becomes a quiet place to wander before drifting off. Tonight, we're going to explore something that sounds simple at first, but becomes more surprising the longer you sit with it. We're going to gently unfold a question that sounds almost childlike in its simplicity. How big is the solar system, really? It's a question that seems like it should have a neat answer, perhaps a number you could write down, something tidy and satisfying. But as we move through it together, you may begin to notice that the idea of size in space is not quite as straightforward as measuring a room or even a country. Distance stretches in unfamiliar ways out there. Familiar reference points fade. The mind tries to hold on to scale, and then, very gradually, lets go. Before we begin, I'd like to ask you something simple. Where are you listening from tonight? And what time is it in your part of the world right now? Maybe it's late evening and the day is winding down. Maybe it's very late, and the quiet has already settled in around you. Wherever you are, I'm glad you're here for this gentle journey outward. If you find this kind of slow, curious exploration soothing, or simply a pleasant way to unwind, you might consider liking the video or subscribing. It helps this calm little corner of science reach others who are also looking for something thoughtful and relaxing at the end of the day. Now let's begin by imagining something familiar. Picture yourself standing outside on a clear night. The air is still. Above you the sky's scattered with stars. Some faint, some bright enough to catch your attention immediately. Somewhere up there, invisible to your eyes, are the planets of our solar system, each following its quiet path around the sun, each separated from the others by distances so large that they almost resist imagination. We often talk about the solar system as if it were a kind of collection, a group of objects gathered together in space, like fruit in a bowl or houses along a street. There's the sun in the middle, then Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and beyond them smaller worlds, icy fragments, distant clouds of debris. It sounds organised, almost compact, as though everything is neatly arranged. But the truth is very different. The solar system is not crowded. It is not tightly packed. In fact, it is overwhelmingly empty. That emptiness is the first clue to understanding its true size. You see, when we look at diagrams in books or animations online, the planets are often shown fairly close together. This isn't because they really are close together, but because if the distances were drawn accurately, the planets would be so far apart that the diagram would need to be impossibly large. You might see Earth drawn a few centimetres from the Sun on a page, and Jupiter perhaps a short distance farther out. But in reality, if the Sun were the size of a large exercise ball, Earth would be a small bead many meters away, and Neptune would be so far off that you might lose sight of it entirely. Our minds are not used to scales like this. We live in a world where walking a few kilometers feels like a journey, where driving across a country can take hours, where crossing an ocean takes a day in an airplane. These distances feel large to us because they are large on a human scale. But in the solar system, even the vast distances between continents would shrink into insignificance, smaller than the thickness of a line on a map. And yet, despite how enormous the solar system truly is, we live right in the middle of it, moving through it constantly, carried along by Earth's orbit without ever feeling the motion. Right now, as you listen, the planet beneath you is travelling around the Sun at about 30 kilometers per second. That's over 100,000 kilometers per hour, fast enough to circle Earth more than twice in a single hour, and yet completely imperceptible. The ground feels steady. The air feels calm. Time moves at its usual pace. It's one of those quiet reminders that motion, like size, often depends on perspective. Thinking about scale in space requires a small adjustment in how we imagine distance. Instead of meters or kilometers, astronomers often use something called an astronomical unit. One astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers. That may sound like a large number, and it is, but it's also a useful stepping stone, a way to make the vastness of the solar system slightly easier to describe. Mercury orbits at about 0.4 astronomical units from the Sun, Venus at about 0.7 astronomical units. Earth, of course, sits at 1 astronomical unit. Mars is around 1.5 astronomical units away. At first, those numbers seem manageable, almost close together, like neighbouring towns along a highway. But then we continue outward. Jupiter orbits at about 5 astronomical units. Saturn at about 9.5 astronomical units. Uranus at roughly 19 astronomical units. Neptune at about 30 astronomical units. Each step outward multiplies the distance, stretching the scale farther and farther, until the inner planets feel clustered together near the Sun like grains of sand near the centre of a vast empty field. What's interesting is that even these numbers don't fully capture the feeling of distance. Numbers can be precise, but they don't always feel real. To really sense the scale, it helps to think in terms of travel time. Light, the fastest thing in the universe, takes just over 8 minutes to travel from the Sun to Earth. That means the sunlight you see right now actually left the Sun 8 minutes ago. If the Sun were to suddenly disappear, which fortunately it won't, we wouldn't know for 8 minutes. To reach Jupiter, sunlight takes about 43 minutes. To reach Neptune, it takes more than 4 hours. Imagine that for a moment. A beam of light, moving at nearly 300,000 kilometers per second, still needs hours to cross the solar system to its outermost major planet. That begins to give a sense of the scale we're dealing with. Another way to think about it is to imagine shrinking the solar system down to a more familiar size. Suppose the Sun were the size of a coin placed on a large field. Earth would be a tiny speck several meters away. Neptune would be hundreds of meters distant, and between them, almost nothing. Just space, silent and empty. That emptiness is one of the defining features of our cosmic neighbourhood. Space is not filled with swirling clouds or glowing light most of the time. It is mostly vacuum, with only occasional particles drifting through. The planets are islands in a vast, dark ocean. And yet, even calling them islands might be misleading, because islands suggest proximity, the possibility of seeing one from another on a clear day. In the solar system, the distances are so great that if you stood on one planet, the others would usually appear as little more than bright points of light, indistinguishable from stars to the naked eye. It's a quiet kind of vastness, not dramatic or overwhelming in the way mountains or storms can be, but subtle, patient, stretching outward in every direction. Sometimes it helps to pause and reflect on how recently humanity has begun to grasp this scale. For most of history, people believed the planets were small lights embedded in a crystal sphere surrounding Earth. The sky felt close, intimate, almost within reach. It wasn't until the last few centuries that we began to understand just how far away those lights truly were. Even now, our intuition struggles to keep up. Think about the moon for a moment. It feels close, familiar, part of our everyday experience. And in cosmic terms, it is close. The moon is about 384,000 kilometers away. Light takes just over 1 second to travel that distance. Astronauts reached it in a few days, but compared to the rest of the solar system, the moon is practically in our backyard. It's the first small step outward, the nearest marker on a journey that quickly becomes far more expansive. As we move farther from Earth, distances begin to grow not just large, but immense. The gaps between worlds widen. Travel times stretch from days to months, then to years. Signals sent from spacecraft take longer and longer to reach us, until conversations with distant probes unfold with minutes or even hours between each reply. There's something quietly humbling about that. It reminds us that the solar system is not a compact arrangement of worlds, but a sprawling, sparsely populated region of space, bound together by gravity yet separated by enormous distances. And yet, despite that vastness, everything within it is connected. Every planet, every asteroid, every comet is held in orbit by the sun's gravity, all of them moving together through the galaxy like a slow, silent caravan. If you imagine the solar system not as a cluster, but as a wide, gently rotating disk, with the sun at its centre and the planets tracing enormous circular paths, the scale begins to feel more natural. Not small, not crowded, but expansive and calm. Right now, Earth is on one of those paths, carrying oceans, continents, cities, forests, and all of us along with it. We rarely think about it, but we are travellers in space, moving through a vast system whose true size is far greater than it first appears. And that realization opens the door to a deeper question. When we ask how big the solar system really is, what exactly are we measuring? Are we talking about the distance to the farthest planet, the edge of the sun's gravitational influence, the boundary where the solar wind fades into interstellar space? When people hear the words the solar system, most of us picture something fairly simple. There's the sun in the middle, the planets arranged in order, maybe a few rings and moons, and beyond that, well, a vague sense of space fading into darkness. It feels like a neat, defined place, almost like a map with a clear border drawn around it. But if you pause for a moment and think about it, that idea of a border becomes a little uncertain. Where exactly would you draw the line? At the orbit of Neptune? At the farthest known dwarf planet? At the point where the sun's gravity finally loses its influence? Or somewhere even farther out, in regions we've never directly seen? It turns out that the solar system doesn't have a single, tidy edge. Instead, it fades outward gradually, like the glow of a campfire dimming into the night. To understand what we mean by the solar system, it helps to start with the most obvious part, the sun itself. The sun contains more than 99.8% of all the mass in the solar system. Everything else, every planet, moon, asteroid and comet combined, makes up only a tiny fraction of what's here. In a sense, this solar system is really the sun's domain, the region of space where its gravity shapes the motion of objects around it. Gravity is the key idea here. The solar system is not defined by visible boundaries, but by influence. Anything that orbits the sun or is strongly controlled by the sun's gravity is part of the solar system. That sounds straightforward at first. The planets clearly orbit the sun, so they're included. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Each follows its own path, taking months or years to complete a single circuit. But already, even at this level, things begin to feel more complex than the simple textbook picture. The planets are only the most visible members of a much larger family. Each planet is surrounded by moons, sometimes dozens of them. Jupiter alone has more than 90 known moons, some large enough to be planets in their own right if they orbited the sun directly. Saturn's rings, which look so smooth and elegant from a distance, are actually made of countless individual pieces of ice and rock, each one orbiting Saturn like a tiny world. And then there are the asteroids, thousands upon thousands of rocky fragments, most of them orbiting between Mars and Jupiter in a region known as the asteroid belt. Some are small as pebbles. Others, like Ceres, are hundreds of kilometers across and nearly spherical. Beyond that lie comets, icy travellers that spend most of their time far from the sun, only occasionally sweeping inward, growing bright tails as sunlight warms their surfaces. All of these objects are part of the solar system, even though many of them are rarely mentioned in simple diagrams. The solar system is not just planets. It is a vast population of bodies of many sizes, most of them small, most of them invisible to the naked eye. And still, that's only the beginning. Because the solar system also includes things you cannot see at all. This solar wind, for example, is a continuous stream of charged particles flowing outward from the sun in all directions. It moves through space, filling the region around the sun with a thin, invisible plasma. That flow extends far beyond the orbits of the planets, forming a kind of enormous bubble around our star. This bubble, called the heliosphere, stretches far into space, much farther than Neptune, much farther than Pluto, reaching distances so large that sunlight itself takes many hours to travel across it. Inside that bubble, the sun's influence dominates. Outside it, the space between the stars begins. So one way to define the solar system is to say that it extends as far as the heliosphere, as far as the solar wind can reach before it is slowed and pushed back by the thin gas of interstellar space. But even that may not be the final edge. Far beyond the planets, beyond the region where most comets originate, astronomers believe there may be a vast spherical cloud of icy objects surrounding the Sun, at distances tens of thousands of times farther than Earth is from the Sun. This region is called the Oort Cloud, and although we cannot see it directly, there is strong evidence that it exists. If the Oort Cloud is real, then the solar system extends astonishingly far, perhaps halfway to the nearest stars. In that sense, the solar system is not a small neighbourhood at all, but a huge diffuse region stretching across distances so large that the inner planets would seem like a tiny speck near the centre. This brings us to an interesting point. The solar system is not a solid thing. It is not a sphere or a disk with clear edges. It is more like a gradient, a gradual thinning of object and influence as you move farther outward. Closer to the Sun, matter is more concentrated. Planets, moons, asteroids, dust and gas are relatively common, at least by cosmic standards. Farther out, objects become fewer and farther between. Eventually, the Sun's gravity becomes so weak that passing stars and the tides of the galaxy begin to compete with it. At that distance, it becomes difficult to say exactly where the solar system ends and interstellar space begins. There is no sharp boundary, no signpost announcing that you've crossed from one region to the other. There is only a gradual transition, a fading of one environment into another. Another way to think about it is to imagine standing at the edge of a forest at night. The trees grow thinner and thinner, until eventually there are only a few scattered trunks, then none at all. Where did the forest end? At the last tree? Or at the point where trees became rare? The answer depends on how you choose to define it. The solar system is like that forest, and definitions matter because depending on which one you use, the size of the solar system changes dramatically. If you define it as the region containing the planets, it extends to about 30 astronomical units, the distance of Neptune. If you include the Kuiper Belt, where Pluto and many icy bodies reside, it stretches to perhaps 50 astronomical units or more. If you include the heliosphere, the solar wind bubble, it reaches more than 100 astronomical units in some directions. And if you include the Oort Cloud, the solar system may extend tens of thousands of astronomical units, a distance so vast that it becomes difficult to comprehend. At that scale, the solar system is no longer something you could easily draw on a page or even model on a football field. It becomes something more like a region of space, diffuse and expansive, defined more by influence than by structure. There's also another subtle point worth considering. The solar system is not stationary, it is moving. Our Sun orbits the centre of the Milky Way galaxy at a speed of about 220 kilometers per second. As it travels, it carries the entire solar system with it. Planets, comets, dust, and all. So the solar system is not just a set of orbits around the Sun, it is also a moving bubble, drifting through the galaxy, passing through regions of varying density and radiation. That motion adds another layer to the idea of what the solar system is. It is not just a place. It is a travelling system, a moving environment shaped by both the Sun and the wider galaxy around it. Sometimes it helps to step back and appreciate how extraordinary it is that we can even ask these questions. Just a few centuries ago, people did not know the true distances to the planets, or even that other stars were suns like our own. The idea of the solar system as a vast, structured region of space is a relatively recent discovery, and even now, our understanding continues to evolve. New dwarf planets are discovered, new comets are tracked. Spacecraft venture farther than any human-made object has gone before, sending back data from regions once thought unreachable. Each new piece of information helps refine our picture of the solar system, making it clearer but also revealing how much more there is to learn. So when we ask how big the solar system really is, we're also asking what we mean by it. Are we measuring the region of planets, the reach of the solar wind, the outermost icy bodies held loosely by the sun's gravity? So let's begin close to home with something solid and familiar, something we can actually picture without straining the imagination too much. Before we try to grasp the size of the solar system, it helps to anchor ourselves to a scale we understand. And there is no better starting point than the planet you're sitting on right now. Earth feels large to us. Oceans stretch beyond the horizon. Flights between continents take many hours. Crossing an entire country can take days by car. For most of human history, the world felt almost immeasurably vast, a place so big that exploring it took lifetimes. And yet, from a cosmic perspective, Earth is small. Not just small in a poetic sense, but physically small, a sphere about 12,742 kilometers in diameter. If you could drive straight through the planet from one side to the other, ignoring the rather impractical detail of molten rock in the way, you would travel a distance roughly equal to the width of the continental United States. That's large on a human scale, certainly, but compared to the distances between worlds, it's only the first tiny step. One useful way to understand Earth's size is to compare it with something we can experience more directly: travel time. A commercial airplane moves at around 900 kilometers per hour. At that speed, flying halfway around the world takes roughly 10 hours. To circle the entire planet would take about twice that, not counting layovers, delays, or the small but inevitable wait at baggage claim. Now imagine shrinking Earth down to the size of a marble. Not a very tiny marble, perhaps one about 2 centimeters across. At that scale, a passenger jet would be far too small to see, and the tallest mountains would be little more than fine texture on the surface. Holding that marble in your hand, it would be easy to forget that it represents everything familiar: every city, every forest, every ocean, every person who has ever lived. The entire human story compressed into something that could roll under a sofa and disappear. Thinking this way helps reset our sense of scale. It reminds us that even the largest things in our everyday experience are small compared to planetary and cosmic distances. Another way to appreciate Earth as a reference point is to think about gravity. Earth's gravity feels strong to us because we live within it constantly. It holds the atmosphere in place, keeps oceans from drifting into space, and gives weight to everything we touch. But Earth's gravitational influence extends far beyond the surface. In fact, it stretches tens of thousands of kilometers into space, gradually weakening with distance. Satellites orbit within this region, some only a few hundred kilometers above the ground, others much farther away. The International Space Station, for example, orbits at about 400 kilometers above Earth's surface. That sounds high, and it certainly is by aviation standards, but on a planetary scale it's barely above the surface at all. If Earth were the size of a basketball, the space station would orbit less than a centimeter above it. That comparison often surprises people. Space, at least the region where most spacecraft operate, is much closer than it feels. Even the boundary where Earth's atmosphere fades into space, sometimes called the Kármán line, is only about 100 kilometers above sea level, a distance that, if you could drive straight upward, you might cover in little more than an hour. So in a sense, space begins not far above us. The vastness we're trying to understand starts surprisingly close to home, and yet despite that proximity, the moment you leave Earth behind, distances begin to grow very quickly. It's interesting to consider how humans first measured the size of Earth itself. Long before satellites or GPS, ancient astronomers used careful observation and simple geometry. One of the most famous examples comes from Eratosthenes, a Greek scholar who lived more than 2,000 years ago. He noticed that at noon on the summer solstice, the sun shone directly down a well in the city of Sion, casting no shadow. But at the same time in Alexandria, a vertical stick did cast a shadow. By measuring the angle of that shadow and knowing the distance between the two cities, he calculated the circumference of Earth with remarkable accuracy. It's a quiet reminder that understanding scale doesn't always require advanced technology. Sometimes it begins with curiosity, patience, and careful thought. From Earth's size, we can begin to build outward, using our planet as a measuring stick. Astronomers often use Earth's diameter, or the distance from Earth to the Sun, as reference points, stepping stones that help bridge the enormous gaps between objects in space. And those gaps grow faster than most people expect. For example, if Earth were shrunk to the size of a marble, the Sun would not be nearby at all. It would be a sphere about 2 meters wide, placed roughly 200 meters away. That's about the length of 2 football fields. Between the marble and the large sphere there would be almost nothing, just empty space. That emptiness is one of the defining characteristics of the solar system. It is not a crowded place. It is mostly space, with small islands of matter scattered here and there. Another way to approach this idea is to think about light again, because light gives us a kind of universal ruler. Light travels incredibly fast, about 300,000 kilometers per second. It can circle Earth more than 7 times in a single second. And yet, even at that speed, it takes time to cross the distances we're talking about. Light takes about 1/10 of a second to circle Earth once. That's quick enough to feel instantaneous, but already that tiny fraction of time hints at how large the planet really is. Signals sent to satellites in high orbit take noticeable fractions of a second to return. Engineers must account for these delays when controlling spacecraft. Even communication across Earth's surface, through fiber optic cables and radio signals, is not truly instantaneous. It feels that way, but physics quietly reminds us that nothing moves infinitely fast. Using Earth as a reference point also helps us understand something else: how thin our environment really is. The atmosphere, which feels vast when you look up at the sky, is actually very shallow compared to the size of the planet. Most of the air we breathe is contained within the first 10 or 15 kilometers above the surface. Beyond that, the air becomes thinner and thinner until it fades into near vacuum. If Earth were the size of a globe in a classroom, the breathable atmosphere would be thinner than a layer of varnish on its surface. That fragile thinness adds another layer of perspective. Everything we depend on exists in a narrow shell surrounding a small planet, orbiting an ordinary star in a system that extends far beyond our everyday awareness. And yet, despite how small Earth is in cosmic terms, it is still large enough to feel enormous to us. That contrast is part of what makes understanding the solar system challenging. We must hold 2 ideas at once: that Earth is vast on a human scale and tiny on an astronomical one. Sometimes it helps to imagine shrinking yourself rather than shrinking the planet. Imagine you're standing on a plane and the Earth beneath you expands until its curvature becomes obvious, until continents and oceans spread out like patterns on a giant sphere. Now imagine rising upward, higher and higher, watching the planet shrink below you. At first, cities fade, then coastlines blur. Eventually Earth becomes a blue and white marble suspended in darkness, small enough to hide behind your thumb. Astronauts have described this experience as both awe-inspiring and strangely calming. From that distance, the borders and divisions that seem so significant on the ground vanish completely. There is only one world, one atmosphere, one fragile sphere of life. That image, sometimes called the overview effect, changes how people think about Earth's place in the universe. It transforms the planet from something vast into something delicate, almost intimate. Because as soon as you leave Earth behind, even the nearest distances begin to stretch beyond what feels comfortable to imagine. Using Earth as our reference point helps us build intuition gradually, one layer at a time. We begin with something we know, something we can picture, and then extend our understanding outward in stages, like stepping stones across a wide river. It's a patient process, and it rewards patience. The more slowly we approach these distances, the more clearly they begin to make sense. Let's move outward now, but only a little, because the first step away from Earth is both modest and astonishing at the same time. Our nearest neighbour in space, the Moon, has been part of human life for as long as people have looked up at the sky. It feels familiar, predictable, almost companionable, rising and setting in its steady rhythm, changing shape night after night in a cycle that guided calendars, harvests and stories for thousands of years. And yet, despite that familiarity, the Moon is far away, much farther than most people instinctively imagine. If you were to get into a car and drive toward the Moon at highway speed, say around 100 kilometers per hour, without stopping to refuel, rest or sleep, it would take you more than 5 months to arrive. Even a jet aircraft flying far faster than any car would need several weeks to make the journey. Light, travelling at the fastest speed possible in the universe, takes just over 1 second to cross the distance between Earth and the Moon. That may not sound like much, but it's long enough that astronauts on the lunar surface experienced a slight delay in radio conversations. When someone on Earth asked a question, there was always a small pause before the reply came back, a reminder that even at the speed of light, space is not truly small. The average distance to the Moon is about 384,000 kilometers. Numbers that large can feel abstract, so it helps to translate them into something more tangible. Imagine Earth as a globe about 1 meter in diameter, roughly the size of a large exercise ball. At that scale, the Moon would be about the size of a tennis ball placed nearly 30 meters away. That's about the length of a swimming pool, or the distance across a wide city street. Between the globe and the tennis ball, there would be nothing. No dust, no rocks, no air, no faint glow, just empty space. That emptiness is the first thing people notice when they begin to grasp the distance to the Moon. The Earth and Moon are often shown close together in illustrations, sometimes with only a small gap between them, but in reality they are separated by a vast stretch of vacuum. There's a fascinating fact that helps make this clearer. All of the planets in the solar system could fit in the space between Earth and the Moon, lined up side by side, and there would still be room left over. Jupiter alone would take up a large portion of that space, but the remaining planets together would still fit comfortably within the gap. It's one of those comparisons that quietly reshapes your sense of scale. The distance to the Moon, which feels modest on an astronomical scale, is already enormous compared to the sizes of the worlds themselves. The Moon's orbit is not perfectly circular, so its distance from Earth changes slightly over time. At its closest, called perigee, it comes within about 363,000 kilometers. At its farthest, called apogee, it can be more than 405,000 kilometers away. That variation is large enough to affect how big the Moon appears in the sky, giving us what people sometimes call a supermoon, when it's slightly closer and brighter than usual. Even so, these changes are small compared to the overall distance. Whether near or far, the Moon remains a remote world, separated from us by a gulf that only a handful of humans have ever crossed. When the Apollo missions travelled to the Moon in the late 1960s and early 1970s, the journey took about 3 days. That may sound quick, but those 3 days unfolded in a spacecraft no larger than a small room, moving through a silence and darkness unlike anything experienced on Earth. Astronauts described looking back and seeing Earth shrink to the size of a marble suspended in blackness, a sight both beautiful and deeply unsettling. For the first time, humans could see their home as a single, fragile world, isolated in space. That journey, as remarkable as it was, covered only a tiny fraction of the distances within the solar system. The Moon is our closest neighbour, the first stepping stone outward, and yet it already stretches our sense of scale. Another way to appreciate this distance is to think about communication. When Mission Control spoke to astronauts on the Moon, each message took about 1.3 seconds to travel one way. Conversations required patience, pauses, and careful timing. It was a subtle but constant reminder that even nearby space is not instantaneous, and yet in cosmic terms the moon is practically next door. To understand why, it helps to think about how gravity shapes the Earth-Moon system. The moon is bound to Earth by gravity, orbiting once every 27.3 days. But Earth also moves slightly in response to the moon's pull. In fact, both bodies orbit a common centre of mass, a point located inside Earth, but not at its centre. This gentle gravitational dance has been going on for billions of years. The tides in Earth's oceans are one visible result, rising and falling as the moon's gravity pulls on the water. Over very long periods of time, the interaction between Earth and Moon is slowly changing the system. The Moon is gradually moving farther away from Earth, drifting outward at a rate of about 3.8 centimeters per year, roughly the speed at which fingernails grow. It's a slow, almost imperceptible change, but over millions of years it adds up. Long ago, the Moon appeared larger in the sky than it does today, and in the distant future it will appear smaller. There's something quietly comforting about that steady motion. The idea that even the distances between worlds are not fixed, but evolve over time, shaped by gravity and motion. The journey to the Moon also teaches us something about the nature of space itself. Between Earth and the Moon, there is no air, no weather, no sound. Space is not like the thin air at the top of a mountain. It is a near-perfect vacuum, emptier than any environment we can create on Earth. That emptiness changes everything about travel. Without air, there is no drag to slow a spacecraft, but also no oxygen to breathe, no atmosphere to shield from radiation, no warmth to retain heat. Temperatures can swing wildly between sunlight and shadow. The silence is complete, broken only by vibrations inside the spacecraft itself. And yet, despite those challenges, humans made the journey, guided by mathematics, engineering, and an extraordinary amount of patience. It's worth pausing for a moment to consider how remarkable that is. For nearly all of human history, the Moon was unreachable, a distant light in the sky. Then, within the span of a single generation, people walked on its surface, left footprints in its dust, and returned safely home. Those footprints are still there today. With no wind or rain to erase them, they may remain for millions of years, quiet marks of a brief human presence on another world. Looking at the Moon from Earth now, it's easy to forget how far away it really is. Our eyes and brains are not well equipped to judge distances in the sky. The Moon appears large because it is relatively close, but it still lies nearly 400,000 kilometers away, far beyond the reach of any aircraft, beyond the atmosphere, beyond the protective magnetic field that shields much of Earth's surface. And yet, in the scale of the solar system, that distance is only the first small step. To put it another way, if Earth and the Moon were separated by 1 meter, the Sun would be about 400 meters away. Jupiter would be more than 2 kilometers distant. Neptune would be over 12 kilometers away. And the outer reaches of the solar system would stretch far beyond that, fading into distances difficult to imagine in everyday terms. So the journey to the Moon, impressive as it is, barely begins to hint at the true size of the solar system. There's also something psychologically interesting about the Moon as a reference point. It's close enough to feel familiar, yet far enough to remind us that space is vast. It sits at the boundary between the world we know and the wider universe beyond, a kind of threshold between Earth and everything else. For early astronauts, crossing that threshold was both exhilarating and sobering. As they moved farther from Earth, the planet filled less and less of the window, shrinking from a world into a sphere, then into a small disk against the blackness. One astronaut described the experience as realizing all at once that everything he had ever known, every place, every person, every memory, was contained in that small distant globe. It's a perspective that changes how you think about size, distance, and place. The Moon may be far, but it's still close enough that Earth dominates the sky from its surface, hanging overhead as a large blue world, nearly 4 times the apparent size of the Moon as seen from Earth. If you stood on the Moon, Earth would not rise and set in the same way the Moon does here. Instead, it would hover in roughly the same part of the sky, slowly changing phases, turning like a luminous marble suspended in darkness. That image, Earth seen from the Moon, helps anchor our sense of scale in both directions. It reminds us that distances in space are large, but also that our home is just one small world among many. Trying to measure distances in space is a bit like trying to measure the width of an ocean while standing on the shore with nothing but a ruler. The scale is so far beyond everyday experience that our usual tools, kilometers and miles, quickly become awkward and difficult to use. The numbers grow so large that they lose their meaning. 1,000,000 kilometers sounds enormous, until you realize that light can travel that distance in just over 3 seconds, and suddenly the number feels smaller than it should. So astronomers had to learn, step by step, how to think about distance differently. They needed ways to measure the universe that made sense at scales, where ordinary intuition begins to slip. One of the earliest methods came from simple geometry, the same careful reasoning that allowed ancient scholars to measure the size of Earth. The key idea is something called parallax. You may have noticed this effect without realizing it has a name. If you hold out your thumb at arm's length and close one eye, then switch eyes, your thumb seems to shift against the background. That apparent movement is parallax, and it happens because each eye sees the world from a slightly different angle. Astronomers realized long ago that the same principle could be used to measure the distance to nearby objects in space. Instead of using 2 eyes, they used Earth's motion around the Sun. 6 months apart, our planet is on opposite sides of its orbit, separated by about 300 million kilometers. From those 2 positions, nearby stars appear to shift slightly against the more distant background stars. By measuring that tiny shift and applying geometry, astronomers can calculate the star's distance. It's an elegant method, quiet and patient, relying on careful observation rather than dramatic technology. Even today, spacecraft like the Gaia Observatory continue to use parallax to map the positions and distances of millions of stars with extraordinary precision. But before astronomers could measure stars, they first had to measure the distances within the solar system itself. And that turned out to be a remarkable challenge. For centuries, people knew the relative order of the planets, but not their actual distances. They could see that Mars sometimes appeared brighter and closer than usual, and that Venus never strayed far from the Sun, but the scale of the system remained unknown. One of the breakthroughs came from observing the transit of Venus, a rare event in which Venus passes directly between Earth and the Sun, appearing as a small black dot moving across the solar disk. By timing this event from different locations on Earth, astronomers in the 18th century were able to use parallax to calculate the distance from Earth to the Sun with surprising accuracy. That distance, about 150 million kilometers, became the foundation for measuring everything else. Astronomers gave it a special name, the astronomical unit, or AU. The astronomical unit is one of the most useful ideas in astronomy because it provides a scale tailored to our own cosmic neighborhood. Instead of saying Jupiter orbits at roughly 778 million kilometers from the Sun, it's much easier to say that Jupiter is about 5.2 astronomical units away. Neptune orbits at about 30 astronomical units. The numbers become smaller, easier to picture, and more meaningful in context. It's similar to how we use hours instead of seconds to measure long stretches of time. Both describe the same quantity, but one is easier to work with. Even with the astronomical unit, however, the solar system remains vast. Spacecraft travelling at tens of thousands of kilometers per hour still take years to reach the outer planets. Signals from distant probes take hours to return. The distances are large enough that time itself becomes part of the measurement. And that leads to another way astronomers think about distance: light travel time. Because light moves at a constant speed, it provides a natural ruler. Instead of saying that the Sun is 150 million kilometers away, we can say that sunlight takes about 8 minutes to reach Earth. Jupiter is about 40 to 50 light minutes from the Sun. Neptune is roughly 4 light hours away. This way of thinking has a quiet clarity to it. It connects distance with experience. When you feel sunlight on your face, you are feeling energy that left the Sun 8 minutes ago. When astronomers observe distant planets, they are seeing them as they were minutes or hours earlier. The farther we look, the further back in time we see. Within the solar system, these delays are modest, but they are real. When engineers send commands to spacecraft orbiting Mars, they must wait several minutes for a response. During that time, the spacecraft continues its work autonomously, guided by instructions sent long before. There is something both practical and poetic about that delay. The idea that even within our own planetary neighbourhood, communication is never instantaneous. Another important method for measuring distances in the solar system is radar ranging. This technique involves sending a radio signal toward a planet or asteroid, and timing how long it takes for the signal to bounce back. Because radio waves travel at the speed of light, the round-trip time reveals the distance with remarkable precision. Radar measurements of Venus in the mid-20th century helped refine the value of the astronomical unit and provided some of the most accurate measurements of planetary distances ever made. What's fascinating about radar ranging is its simplicity. The principle is the same as shouting in a canyon and listening for the echo, except the distances are measured in millions of kilometers, and the echoes are faint radio signals returning from distant worlds. Over time, astronomers developed an entire ladder of methods for measuring distance, each one suited to a different scale. Parallax works well for nearby stars. Standard candles, objects with known brightness, help measure more distant regions of the galaxy. Redshift reveals the expansion of the universe at the larger scales. But here in the solar system, the astronomical unit and light travel time remain the most intuitive tools. It's worth pausing for a moment to consider how extraordinary this is. Human beings, living on a small planet, have found ways to measure distances across billions of kilometers using nothing more than geometry, light, and careful observation. We've turned the universe into something measurable, not by shrinking it, but by expanding our understanding. And yet, even with these tools, distance in space can still feel abstract. Numbers alone rarely capture the emotional sense of scale. That's why astronomers and educators often use models to help people visualize the solar system. One common model imagines shrinking the Sun to the size of a grapefruit. At that scale, Earth would be a grain of sand about 15 meters away. Jupiter would be another small sphere about 75 meters from the grapefruit, and Neptune would be more than 400 meters away, far enough that you might lose sight of the model's center. Between these objects there would be long stretches of empty ground. Walking from one planet to another would take time, and that time helps the mind grasp the distances involved. Some museums and science centers have built walking-scale solar system models where each step represents millions of kilometers. Visitors begin at a large sculpture of the Sun and then walk, sometimes for several minutes, before reaching the first tiny marker representing Mercury. By the time they reach the outer planets, the walk may have covered hundreds of meters or more. People often remark on the same thing after experiencing these models: the emptiness, not the size of the planets, but the vast, quiet gaps between them. Those gaps are what truly define the solar system. Another subtle but important aspect of measuring space is uncertainty. Distances in astronomy are rarely perfectly precise. Orbits are slightly elliptical. Gravitational influences from other bodies cause small variations. Measurements improve over time as instruments become more accurate. Astronomy is, in many ways, a science of patience. Observations accumulate gradually. Data is refined. Models are updated. Over years and decades, our picture of the solar system becomes clearer and more detailed. Even now, spacecraft continue to refine our understanding. Missions to Mars, Jupiter, and beyond provide precise tracking data, that improves our knowledge of planetary positions and distances. The farther we explore, the better our measurements become. And yet, despite all this precision, there remains a sense of wonder in the simple fact that space is so large that it requires its own units of measurement, its own ways of thinking, its own patience. Once you begin to think in astronomical units and light minutes, the solar system starts to feel less like a collection of nearby worlds and more like a vast landscape, one where distances are measured not in steps or kilometers, but in the time it takes light to travel. Moving farther outward from Earth, the solar system begins to open up in a way that can feel surprising. Many of us grow up with diagrams showing the inner planets neatly lined up, orbiting the Sun in a compact arrangement, almost like beads on a string. Mercury sits closest, then Venus, then Earth, then Mars, all within what looks like a fairly small region before the asteroid belt appears like a boundary marking the next stage. But once you begin thinking in real distances instead of simplified drawings, that apparent closeness begins to dissolve. The inner solar system is not crowded at all. It is a region of scattered worlds, each separated by enormous stretches of empty space, each moving along its own path around the Sun, rarely coming anywhere near one another. To picture this more clearly, it helps to return briefly to the idea of the astronomical unit, the average distance between Earth and the Sun. At 1 astronomical unit, Earth sits comfortably in what astronomers call the habitable zone, where temperatures allow liquid water to exist. Mercury orbits at about 0.4 astronomical units, Venus at about 0.7 astronomical units, and Mars at about 1.5 astronomical units. Those numbers may look close together, but they conceal vast gaps. The distance from Earth to Venus at their closest approach is tens of millions of kilometers. The distance from Earth to Mars, even at its nearest, is still tens of millions more. Most of the time, the planets are much farther apart. Imagine placing the Sun in the centre of a large park as a sphere about 1 metre wide. Mercury would be a tiny speck roughly 40 metres away. Venus would be about 70 metres from the Sun. Earth would be about 100 metres away, and Mars roughly 150 metres out. Between each of those points, there would be nothing but open ground. If you were walking from one to another, the journey would feel long and quiet. There would be no visible path, no markers, only empty space between distant objects. That emptiness is the true character of the inner solar system. Mercury, the innermost planet, circles the Sun in just 88 days. It moves quickly, racing along its orbit at nearly 48 kilometers per second, faster than any other planet. From the Sun, Mercury would appear as a small, rocky world baked by intense heat, its surface marked by craters that have remained unchanged for billions of years. Because Mercury is so close to the Sun, it experiences extreme temperature swings. The side facing the Sun becomes incredibly hot, while the side in darkness grows intensely cold. With almost no atmosphere to distribute heat, the contrast is stark. It is a world of harsh sunlight and deep shadow, orbiting in silence. And yet, even Mercury is not close to the Sun in the way we might instinctively imagine. If the Sun were 1 metre across, Mercury's orbit would still be dozens of metres away, far enough that the Sun would appear large in its sky but not overwhelming. Moving outward, we reach Venus, often called Earth's sister planet because of its similar size. But in reality, Venus is a very different world, wrapped in thick clouds of carbon dioxide, with surface temperatures hot enough to melt lead. The atmosphere there is so dense that the pressure at the surface is more than 90 times that of Earth's atmosphere at sea level. Venus orbits the Sun more slowly than Mercury, taking about 225 Earth days to complete a single revolution. From space, it appears bright and reflective, its cloud layers bouncing sunlight back into space, making it one of the most brilliant objects in our night sky. Despite being the closest planet to Earth in terms of orbital distance, Venus is still unimaginably far away in human terms. Spacecraft travelling to Venus take months to arrive, following carefully calculated trajectories that use the motion of both planets to minimise fuel use. Then there is Earth, our reference point, a world with oceans, weather and life, orbiting in a relatively stable and temperate zone. From here, the distances between planets feel abstract, because we rarely experience them directly, but spacecraft remind us of their scale. Even a journey to Mars, our nearest outer neighbour, requires many months of travel. Mars itself orbits at about 1.5 astronomical units from the Sun. It is smaller than Earth, colder, with a thin atmosphere and vast deserts of iron-rich dust that give it its reddish colour. Robotic explorers have been studying Mars for decades, sending back images of ancient river valleys, towering volcanoes and landscapes that look strangely familiar, yet unmistakably alien. What's striking about Mars is not just its distance from Earth, but the variability of that distance. Because both planets move along their own orbits, sometimes they are on the same side of the Sun and relatively close, and other times they are on opposite sides, separated by hundreds of millions of kilometres. This changing geometry means that missions to Mars must be carefully timed, launching during windows that occur roughly every 26 months when the two planets are favourably aligned. Even then, the journey typically takes 6 to 9 months. That's another quiet reminder of scale. The nearest planet that humans might realistically visit lies many months away, even with modern technology. Looking at the inner solar system as a whole, what stands out is how small the planets are compared to the distances between them. If you were drifting through this region in a spacecraft, you could travel for days or weeks without seeing anything larger than a distant point of light. Space is not like the crowded scenes often shown in science fiction, where ships weave between planets and asteroids in a matter of minutes. In reality, the solar system is mostly empty. The planets are separated by vast expanses of vacuum, and encounters between objects are rare on human timescales. Even the asteroid belt, which many people imagine as a dense field of tumbling rocks, is mostly empty space. The asteroids are spread over such a large region that a spacecraft can pass through without seeing any nearby objects at all, unless it deliberately navigates toward one. That sense of isolation becomes clearer when you consider how the planets would appear from one another. From Mars, Earth is visible as a bright star-like point. From Venus, Earth appears similarly small, though sometimes bright enough to cast faint shadows. None of the planets loom large in one another's skies the way the Moon appears from Earth. The distances are simply too great. There's also a deeper pattern to the inner solar system, one that astronomers believe reflects its formation billions of years ago. Close to the Sun, temperatures in the early solar nebula were high, allowing only rock and metal to condense into solid bodies. Farther out, beyond a certain distance, ices could form, leading to the creation of much larger gas-rich planets. This is why the inner planets are small and rocky, while the outer planets are enormous and composed largely of gas and ice. The boundary between these regions lies somewhere beyond Mars, near the area we now call the asteroid belt. Understanding that history helps explain why the inner solar system looks the way it does. A handful of relatively small worlds orbiting in a broad, mostly empty region, with the Sun dominating everything at the centre. The Sun itself, even at these distances, remains the most prominent object in the sky of every inner planet. From Mercury, it appears more than twice as wide as it does from Earth. From Mars, it looks slightly smaller but still brilliant, casting sharp shadows across the dusty surface. That steady presence of the Sun ties the inner planets together. Each one is bound by its gravity, following an orbit determined by a balance between motion and attraction, falling endlessly around the Sun rather than into it. It's a graceful kind of motion, silent and continuous, going on for billions of years without interruption. Sometimes it helps to think of the inner solar system not as a cluster of planets, but as a vast circular track with each world moving along its lane at its own pace. Mercury races along the innermost track, completing a lap in less than 3 months. Venus takes about 7.5 months. Earth takes a year. Mars takes nearly 2. If you could watch from far above, you would see a slow, intricate dance, each planet tracing its path, sometimes drawing closer to another, sometimes drifting farther away, all bound by the same central star. Somewhere beyond the orbit of Mars, the inner solar system begins to give way to something different. Up to this point, the planets we've considered, Mercury, Venus, Earth, and Mars, feel almost like neighbours in a broad but still recognisable region. The distances are large, but they are not yet overwhelming. The travel times between worlds, measured in months, are still within the range of human planning and imagination. Then, gradually, you reach a region where the sense of scale begins to change. This region is known as the asteroid belt, a vast zone stretching roughly from about 2.1 to 3.3 astronomical units from the Sun. On a diagram, it often appears as a thick ring of rocks crowded together, sometimes shown as a dense field of tumbling boulders, as if spacecraft would have to weave carefully to avoid collisions at every turn. In reality, it is nothing like that. The asteroid belt is enormous, and the objects within it are separated by distances so great that a spacecraft can pass through without encountering anything at all, unless it deliberately aims for a target. The typical distance between sizable asteroids can be hundreds of thousands or even millions of kilometers, so why does the asteroid belt matter so much when thinking about the size of the solar system? Because crossing it marks the first moment when distances begin to feel truly vast. Not just large, but expansive in a way that reshapes intuition. The belt itself contains millions of objects, ranging from tiny grains of dust to dwarf planets hundreds of kilometers across. The largest body there is Ceres, about 940 kilometers in diameter, large enough to be spherical under its own gravity, and now officially classified as a dwarf planet. Other notable asteroids like Vesta, Pallas, and Hygeia are substantial worlds in their own right, remnants of the early solar system that never merged into a full-size planet. Astronomers believe that the asteroid belt formed from material that was prevented from coalescing into a planet by the gravitational influence of Jupiter. Jupiter's enormous mass stirred the region, increasing the velocities of nearby objects and making collisions more destructive than constructive. Instead of forming a single large body, the material remained scattered, leaving behind the belt we see today. But what's most striking about the asteroid belt is not the number of objects in it, but the amount of space between them. If you imagine shrinking the solar system down to a scale where Earth's orbit is about 100 meters from the Sun, the asteroid belt would begin roughly 210 meters out and extend to about 330 meters. Within that broad annulus, the asteroids themselves would be tiny, often no larger than grains of sand or pebbles at that scale, separated by distances of many meters or more. Walking across that region would feel like crossing a vast empty field where only occasionally you might notice a small stone on the ground. Spacecraft that have travelled through the asteroid belt, such as the Pioneer and Voyager probes, did not encounter swarms of rocks or hazardous clouds. They passed through quietly, entering and leaving the region without incident. Later missions like Dawn, which orbited both Vesta and Ceres, demonstrated just how sparse the belt truly is. And yet, even though it is mostly empty, the asteroid belt serves as an important psychological boundary. It marks the transition between the inner rocky planets and the outer giants, between a region where the Sun still feels relatively close and one where distances begin to stretch dramatically. To appreciate this, consider the distance from Mars to the inner edge of the asteroid belt. Even at its closest, Mars lies about 1.5 astronomical units from the Sun, while the belt begins beyond 2 astronomical units. That gap alone is roughly the same as the distance from Earth to the Sun. In other words, there is an entire Earth-Sun distance of mostly empty space between Mars and the asteroids. and then the belt itself spans another astronomical unit or more. This is where the true scale of the solar system starts to emerge. The inner planets, which once seemed widely spaced, begin to feel clustered together near the Sun, like a small group of stones at the centre of a wide plain. Another way to sense this scale is to think about travel times. A spacecraft heading toward Jupiter must first cross the distance to Mars, then traverse the wide gulf to the asteroid belt, then pass through it, and only then continue outward into even greater distances. Each stage takes months or years. Signals sent from spacecraft in the belt take tens of minutes to reach Earth. The Sun, still bright, appears noticeably smaller than it does from Earth, though it remains the dominant light in the sky. For early spacecraft engineers, reaching the asteroid belt was once considered a significant milestone. It marked the first step into the deeper solar system, a point where missions moved beyond the relatively familiar territory near Earth and began exploring regions never before visited. There is also something quietly evocative about the asteroid belt as a place. It is a region of remnants, fragments left over from the formation of planets billions of years ago. Each asteroid is a time capsule, preserving clues about the early solar system, about the processes that built worlds and shaped their orbits. Some asteroids are rich in metals, others in silicates, others in carbon compounds. Some contain water locked in minerals, hinting at the role these objects may have played in delivering water to the early Earth. So while the belt may seem empty, it is far from uninteresting. It is a region filled with history, scattered across enormous distances. Another subtle effect of moving outward through the asteroid belt is the changing appearance of the Sun. From Earth, the Sun dominates the sky, bright and intense. From Mars, it is already slightly smaller. From the middle of the asteroid belt, it appears noticeably reduced, still brilliant but no longer overwhelming. Light and heat diminish with distance, following the inverse square law. Double the distance from the Sun, and the sunlight becomes only 1/4 as intense. By the time you reach the outer edge of the asteroid belt, sunlight is less than 1/5 as strong as it is on Earth. That gradual fading of sunlight adds to the sense of moving outward, of leaving the inner solar system behind and entering a region where the Sun's warmth and brightness are less dominant. Crossing the asteroid belt, then, is not just a physical journey, but a conceptual one. It is the point where the solar system begins to reveal its true proportions, where the inner planets shrink into a compact region near the Sun, and the outer system opens up into distances that are harder and harder to imagine. If you are travelling outward, this is the moment when the familiar begins to fade, when the Sun grows smaller, when the gaps between worlds widen, and when the realization begins to settle in that the solar system is far larger than it first appeared. Beyond the scattered expanse of the asteroid belt, the character of the solar system changes in a way that is difficult to appreciate until you really slow down and think about it. Up to this point, the planets we've talked about have been relatively small, rocky, and not so different from one another in size. The distances between them have been large, certainly, but still manageable in the sense that a spacecraft can cross them in months or a few years. Then Jupiter comes into view, and the scale of everything shifts. Jupiter is enormous, not just slightly larger than Earth or Mars, but truly immense. Its diameter is about 143,000 kilometers, more than 11 times that of Earth. You could line up more than 11 Earths side by side across Jupiter's width, and there would still be a little room left over. In terms of volume, Jupiter could hold more than 1,300 Earths inside it. And yet, despite that size, Jupiter is still only a small part of the solar system. What makes its presence so important is not just its physical scale, but its distance from the Sun and from the inner planets. Jupiter orbits at an average distance of about 5.2 astronomical units. That means it is more than 5 times farther from the Sun than Earth is. Light from the Sun takes about 43 minutes to reach Jupiter, compared to just over 8 minutes to reach Earth. That difference alone begins to stretch the imagination. If you were standing on a spacecraft approaching Jupiter, looking back toward the Sun, it would already appear noticeably smaller than it does from Earth, though still bright enough to dominate the sky. The warmth of sunlight would be much weaker. Solar panels, so effective near Earth, become less practical out there, which is why many spacecraft travelling to Jupiter rely on nuclear power instead. The journey to Jupiter also takes time in a way that feels more substantial. Spacecraft do not simply fly straight there in a few weeks. They follow carefully planned trajectories, sometimes using gravity assist from other planets to gain speed. Even with these techniques, a mission to Jupiter typically takes several years. That long travel time reveals something important. The solar system is not just large in distance, but in duration. To move through it requires patience. Signals take longer to travel. Journeys unfold slowly. Exploration becomes measured not in days or months, but in years and decades. There's also a striking change in how space itself feels as you move outward. Inside the orbit of Mars, the sun dominates everything. Its light fills the sky. Its warmth defines the environment of every world. But by the time you reach Jupiter, the sun has begun to lose some of that dominance. It is still powerful, still the central force shaping the system, but it no longer feels close. The sky grows darker. The distances between objects become more apparent. The inner planets, clustered near the sun, would appear as faint points of light, barely distinguishable from stars. Jupiter itself, however, more than makes up for the fading presence of the sun. It is a world of immense storms, swirling cloud bands, and a magnetic field so powerful that it traps radiation in vast belts surrounding the planet. Its Great Red Spot, a storm larger than Earth, has been raging for centuries. Orbiting Jupiter is a system of moons that almost feels like a miniature solar system of its own. The four largest moons, Io, Europa, Ganymede, and Callisto, are substantial worlds in their own right. Ganymede is larger than the planet Mercury. Europa hides an ocean beneath its icy surface. Io is the most volcanically active world known, its surface constantly reshaped by eruptions driven by tidal forces. Standing in the Jovian system, you would see multiple moons rising and setting, casting shadows on the planet's cloud tops, forming a dynamic and ever-changing sky. And yet, as impressive as Jupiter is, what truly begins to feel unreal is not the planet itself, but the distances beyond it. Because once you reach Jupiter, you're still only partway through the planetary region of the solar system. Saturn lies nearly twice as far from the Sun as Jupiter does. Uranus lies nearly twice as far as Saturn. Neptune lies still farther, at about 30 astronomical units from the Sun. Each step outward multiplies the scale in a way that becomes increasingly difficult to grasp. The gaps between orbits widen. The time required to travel between them grows longer and longer. Light itself begins to take hours to cross the distances involved. To put this into perspective, imagine that the distance from the Sun to Earth were reduced to 1 meter. At that scale, Jupiter would be just over 5 meters away. Saturn would be about 10 meters out. Uranus would be nearly 20 meters distant, and Neptune about 30 meters away. Those numbers may not sound enormous, but remember that at this scale Earth itself would be only about 9 millimeters across, smaller than a pea. The planets would be tiny, scattered objects separated by long stretches of empty space, and beyond Neptune, the distances continue to grow. One of the most striking things about the outer solar system is how empty it is. Between Jupiter and Saturn, there is an average gap of more than 650 million kilometers. Between Saturn and Uranus, the distance is even greater. These are expanses so vast that if you were travelling through them, days or weeks could pass without seeing anything but the distant sun and the faint stars. There is a kind of quiet to that emptiness, a stillness that is hard to imagine from our busy, crowded world. Another way to sense this scale is to think about communication again. Signals sent from spacecraft near Jupiter take roughly 35 to 50 minutes to reach Earth, depending on the relative positions of the planets. That means every command, every piece of data, every image arrives with a significant delay. Engineers operating missions in the outer solar system must plan carefully, anticipating problems long before they occur, because real-time control becomes impossible. Spacecraft must often make decisions on their own, guided by instructions sent hours earlier. This separation in time and distance reinforces the feeling that these regions are remote in a way that Mars and the Moon are not. They belong to a different scale of exploration. Jupiter also marks an important boundary in another sense. Its immense gravity has shaped the solar system in profound ways. It acts as a kind of gatekeeper, influencing the paths of comets, deflecting some toward the inner planets, while ejecting others entirely from the solar system. Without Jupiter, the history of Earth might have been very different. Some scientists believe that Jupiter's presence has reduced the number of catastrophic impacts in the inner solar system, though the details are still debated. What is certain is that Jupiter's gravitational reach extends far beyond its own orbit, shaping regions millions of kilometers away. In that sense, Jupiter is not just another planet. It is a dominant feature of the solar system, second only to the Sun in its influence, and yet, even Jupiter is only one step along a much longer journey outward. When spacecraft like Voyager 1 and Voyager 2 passed Jupiter in the late 1970s, they used its gravity to slingshot themselves towards Saturn and beyond, gaining tremendous speed. Those missions revealed something that is easy to overlook when thinking about the solar system from a distance. Reaching Jupiter is not the end of the journey. It is the beginning of a much longer passage into regions where sunlight grows faint and distances become harder and harder to imagine. Out there, the sun shrinks to a brilliant star, still brighter than any other, but no longer filling the sky. Shadows soften. The energy available from sunlight drops dramatically. Temperatures fall, and yet even in that cold and distant realm, the solar system continues, stretching outward far beyond the orbits of the giant planets, into regions filled with icy bodies and distant remnants of its formation. There is a psychological shift that happens when you think about these distances carefully. At first, the solar system seems like a collection of planets orbiting a star, but as you move outward, it begins to feel more like a vast territory, a region of space defined not by objects, but by the enormous gaps between them. Those gaps are the true measure of its size. Jupiter helps reveal that truth because it stands at a kind of threshold. Inside its orbit, the planets are relatively close together, clustered near the Sun. Beyond Jupiter, the solar system opens up, the distances widen, and the sense of scale deepens. If you were travelling outward, this would be the point where the journey begins to feel truly long, where turning back would already require years, where the inner planets would fade into faint points of light near the Sun. Continuing outward from Jupiter, the solar system becomes quieter in a way that is difficult to appreciate until you slow down and imagine the journey carefully. Jupiter already feels distant, already marks a region where the Sun begins to shrink and travel, times stretch into years. But beyond Jupiter lies an even larger realm, where the spaces between worlds grow wider, the sunlight fades further, and the sense of isolation deepens with every astronomical unit. The next world outward is Saturn, orbiting at an average distance of about 9.5 astronomical units from the Sun. That means Saturn is nearly twice as far from the Sun as Jupiter is, and about 10 times farther than Earth. Sunlight there is only about 1% as strong as it is on Earth. The Sun, seen from Saturn, still shines brightly, but it appears smaller, less dominant, more like an intense lamp than the overwhelming disk we see from home. Saturn is famous for its rings, wide and luminous, stretching tens of thousands of kilometers across, yet astonishingly thin. In many places only a few tens of meters thick. From a distance, the rings appear solid, like a shining disk encircling the planet, but up close they are made of countless particles of ice and rock, each orbiting Saturn independently, each following its own path in a silent and delicate dance. If you could drift among those ring particles, the experience would not feel crowded. The pieces are separated by distances that, in many regions, are measured in meters or even tens of meters. It would feel more like floating in a slow-moving snowstorm than navigating a solid structure. Saturn's moons add another layer of complexity to this distant system. Titan, its largest moon, is larger than the planet Mercury and possesses a thick atmosphere rich in nitrogen, with lakes and rivers not of water, but of liquid methane and ethane. Enceladus, another moon, hides a global ocean beneath its icy crust and sends plumes of water vapor into space, hinting at the possibility of habitable environments far from the sun's warmth. Standing in orbit around Saturn, looking outward, the solar system would already feel enormous. Jupiter would be a distant point of light. The inner planets would be invisible without telescopes. Earth itself would appear as nothing more than a pale dot, lost among the stars. And yet, even at Saturn's orbit, you're still far from the edge of the planetary system. Beyond Saturn lies Uranus, a world so distant that sunlight takes nearly 3 hours to reach it. Uranus orbits at about 19 astronomical units from the Sun, roughly twice the distance of Saturn. By the time you arrive there, the Sun appears small and sharp, a brilliant star rather than a blazing disk. Uranus is an unusual planet in many ways. It rotates on its side, tilted by about 98 degrees so that its poles spend long periods facing directly toward or away from the Sun. Seasons there last for decades. For years at a time, one hemisphere remains in continuous daylight while the other remains in darkness. The colour of Uranus, a pale blue-green, comes from methane in its atmosphere, which absorbs red light and reflects blue. It is a quiet world, without the dramatic banding of Jupiter or the bright rings of Saturn. Its rings are faint and narrow, discovered only in the late 20th century. The distance to Uranus reveals something important about the outer solar system. The gaps between planets are not just large, they are immense. The distance from Saturn to Uranus is about 1.4 billion kilometers, nearly 10 times the distance from Earth to the Sun. Crossing that gulf takes spacecraft many years. During that long passage, there is almost nothing to see. The Sun shrinks slowly behind you. The stars remain fixed. The vastness between worlds becomes more apparent than ever. And still, beyond Uranus, there is Neptune. Neptune orbits at about 30 astronomical units from the Sun, more than 30 times farther out than Earth. Sunlight takes about 4 hours to reach Neptune, and by the time it arrives, it is faint, only about 1/900th as intense as the sunlight on Earth. From Neptune's clouds, the Sun would appear no larger than a bright star, though still bright enough to cast faint shadows. The sky would be dark even at noon, illuminated only by that distant point of light. Neptune is a world of deep blue colour and powerful winds, some of the fastest in the solar system, reaching speeds of more than 2,000 kilometers per hour. Storm systems appear and disappear in its atmosphere, driven by internal heat rather than sunlight, because so little solar energy reaches that far. Its largest moon, Triton, orbits in the opposite direction of Neptune's rotation, suggesting that it was once an independent object captured by Neptune's gravity. Triton's surface is cold beyond ordinary experience, with temperatures near -235 degrees Celsius. Nitrogen geysers occasionally erupt there, sending dark plumes across the frozen landscape. Standing in the outer solar system, somewhere near Neptune, the sense of silence would be profound. The Sun would be distant, the inner planets invisible, the stars sharp and steady, unblinking in the darkness. There is a kind of stillness that comes with such distances, a feeling that space is no longer just large, but immense in a way that begins to challenge imagination itself. And yet, even Neptune does not mark the end of the solar system. That's one of the most surprising facts about our cosmic neighbourhood. The region of planets that most people think of when they imagine the solar system, from Mercury to Neptune, occupies only a small portion of its true extent. Beyond Neptune lies another vast region, filled with icy bodies and dwarf planets, a zone that stretches tens of astronomical units farther out. This region is known as the Kuiper Belt, and it is home to Pluto and many other distant worlds. To appreciate the scale involved, consider this. If the distance from the Sun to Neptune were represented by 30 steps, the Kuiper Belt would extend many steps farther still, and beyond that lies an even more distant region, the hypothetical Oort Cloud, which may stretch tens of thousands of astronomical units into space. In other words, the planetary system we've just travelled through, from Mercury to Neptune, is only the inner core of a much larger structure. There is something quietly humbling about that realisation. The planets feel so far apart, their orbits so wide, their travel times so long, and yet they occupy only a small fraction of the Sun's gravitational domain. Another way to sense the scale is to think about the Voyager spacecraft. Voyager 2, the only spacecraft to have visited Uranus and Neptune, was launched in 1977. It reached Neptune in 1989, 12 years later. 12 years of travel to cross the outer planetary system, moving faster than any human-made object had before. And even after passing Neptune, Voyager continued onward, still travelling today, decades later, moving through the outermost regions of the solar system. That journey reveals the true size of our cosmic neighbourhood. It is not a compact cluster of planets, but a vast expanse of space, stretching far beyond the worlds we can easily name. The outer planets, Saturn, Uranus, and Neptune, serve as milestones along that expanse, markers of distance rather than boundaries. They remind us that the solar system is not defined by where the planets end, but by where the Sun's influence fades into the broader galaxy. If you were travelling outward, passing Neptune, you would not encounter a wall or a sudden change. The planets would simply fall behind one by one until the nearest large world was billions of kilometres away, and the solar system would begin to feel less like a system of planets and more like a vast region of space. Beyond the orbit of Neptune, the solar system does not suddenly end. There is no clear boundary, no abrupt transition from planets to empty space. Instead, the environment changes gradually, almost quietly, as though the solar system is thinning out rather than stopping. This region just beyond Neptune is known as the Kuiper Belt, a vast expanse filled with icy bodies, dwarf planets, and countless smaller fragments left over from the formation of the solar system. It begins at roughly 30 astronomical units from the Sun and extends outward to about 50 astronomical units, though its edges are not perfectly sharp. At first glance, it might be tempting to imagine the Kuiper Belt as similar to the asteroid belt, just farther away and colder, but the comparison only goes so far. The asteroid belt lies between the inner and outer planets, relatively narrow in scale, influenced strongly by Jupiter's gravity. The Kuiper Belt, by contrast, is far larger and far more distant, occupying a region of space that dwarfs the entire inner solar system. To appreciate this, it helps to think about the distances involved. Neptune orbits at about 30 astronomical units. The outer edge of the Kuiper Belt may lie near 50 astronomical units. That means the belt itself is about 20 astronomical units wide, nearly the same span as the entire region from the Sun to Uranus. And yet, despite its enormous size, the Kuiper Belt is mostly empty. The objects within it are separated by vast distances, much like the asteroids, but on an even grander scale. A spacecraft travelling through the belt might pass for weeks or months without seeing anything larger than a faint speck in the distance. This emptiness is part of what makes the Kuiper Belt so fascinating. It is not a crowded ring of debris, but a sparse, cold frontier where the Sun's influence is still present but noticeably weaker. Sunlight there is faint, about 1/2000th as intense as on Earth. The Sun itself appears small, bright, but no longer dominant in the sky. Shadows are soft. The warmth of sunlight is barely perceptible. Temperatures in the Kuiper Belt are extremely low, often below -220 degrees Celsius. And yet, even in this cold and distant region, there are worlds. Pluto is perhaps the most famous of them, a dwarf planet about 2,377 kilometers in diameter, smaller than Earth's moon but large enough to have mountains, plains, and a thin atmosphere that freezes and thaws as it moves along its elongated orbit. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a landscape far more complex than anyone had expected. There were glaciers of nitrogen ice, towering mountains of water ice, and vast plains so smooth that they appeared geologically young. It was a reminder that even small worlds in the distant solar system can be dynamic and intriguing. But Pluto is only one of many objects in the Kuiper Belt. There are others: Eris, Haumea, Makemake, and many more. Some nearly as large as Pluto, others much smaller. Astronomers estimate that there may be hundreds of thousands of objects larger than 100 kilometers across, and countless smaller ones. These objects are remnants, leftovers from the early solar system that never merged into larger planets. In a sense, the Kuiper Belt is a fossil record, preserving material from billions of years ago, material that has remained largely unchanged in the cold and darkness. The orbits of these objects are also different from those of the planets. While the planets follow relatively flat circular paths, many Kuiper Belt objects have elongated or tilted orbits, influenced by Neptune's gravity and by the complex history of planetary migration early in the solar system's history. That history is an important part of the story. Astronomers believe that the giant planets did not form exactly where they are today. In the early solar system, Jupiter, Saturn, Uranus, and Neptune may have migrated outward, scattering smaller objects as they moved. Some of those objects were ejected entirely, flung into interstellar space. Others were pushed into distant orbits, forming the Kuiper Belt and perhaps even the much more distant Oort Cloud. So the Kuiper Belt is not just a collection of icy bodies, it is evidence of the solar system's past, a record of the gravitational reshaping that took place long before Earth formed its oceans or life began to emerge. Another subtle but important change occurs as you move into the Kuiper Belt. The Sun's gravitational pull, while still dominant, is no longer overwhelmingly strong compared to other influences. Passing stars, the tidal forces of the Milky Way galaxy, and other subtle effects begin to matter more. This is what it means to say that the Sun begins to lose its grip. Not that its gravity disappears, but that its control becomes less absolute. Objects in the Kuiper Belt are still bound to the Sun, still orbiting it, but their orbits can be more easily perturbed, more easily altered over long periods of time. The solar system, in this sense, becomes less like a tightly bound system and more like a wide, diffuse region, with objects scattered across enormous distances. If you were travelling outward through the Kuiper Belt, the journey would feel very different from travelling among the planets. There would be no large worlds dominating the view, no bright rings or massive cloud tops, only occasional distant objects, faint and cold, drifting in the darkness. The silence would feel deeper, the emptiness more complete. And yet, the Kuiper Belt is still part of the solar system, still within the Sun's domain. Spacecraft like New Horizons continue to explore this region, sending back data from objects billions of kilometers away. Signals from New Horizons take more than 6 hours to reach Earth, a reminder of just how far it has travelled. There is something quietly astonishing about that. A small machine, built on Earth, moving through a region so distant that sunlight itself has grown faint, still able to communicate across billions of kilometers of empty space. That connection, that thin thread of radio waves linking Earth to a spacecraft at the edge of the planetary system, is one of the ways we measure and understand the scale of the solar system. Long before spacecraft ever reached the distant frontier beyond Neptune, Pluto was little more than a faint point of light in a telescope, moving slowly against the background of stars. When it was discovered in 1930, astronomers believed they had found the 9th planet, a lonely world marking the outer edge of the solar system. For decades, Pluto held that role in textbooks and in people's imaginations, the last known stop before the darkness between the stars. At the time, the solar system felt smaller in a conceptual sense. 8 planets near the Sun, and then Pluto, far away but still part of a neat sequence. The idea of a boundary was comforting, as if the solar system was something contained and well-defined. But as telescopes improved and surveys of the outer regions became more thorough, astronomers began to notice that Pluto was not alone. Other objects, faint and distant, were being discovered in similar orbits, sometimes nearly as large as Pluto itself. The picture began to change. Pluto was not the outermost planet after all. It was one member of a much larger population. Understanding this shift requires thinking again about scale. Pluto's average distance from the Sun is about 39 astronomical units, but its orbit is highly elliptical, carrying it as close as about 30 astronomical units, and as far as nearly 50. That means there are times when Pluto actually comes closer to the Sun than Neptune does, though the two never approach each other closely because their orbits are tilted in different planes. This elongated orbit is one of the clues that Pluto is different from the classical planets. The planets follow relatively flat, nearly circular paths around the Sun. Pluto's orbit is tilted and stretched, more like those of many Kuiper Belt objects than like those of the major planets. And that similarity turned out to be important. As astronomers continued to search the outer solar system, they discovered other worlds of comparable size. One of the most significant was Eris, found in 2005, slightly more massive than Pluto and orbiting even farther from the Sun. The discovery of Eris forced scientists to confront a difficult question. If Pluto was a planet, should Eris also be considered one? And if so, how many more planets might there be waiting to be found? Rather than expanding the list indefinitely, astronomers chose to refine the definition of a planet. In 2006, the International Astronomical Union introduced the category of dwarf planets, and Pluto was reclassified accordingly. It remained an important world, but it was no longer considered one of the major planets. For many people, this change felt surprising, even disappointing. Pluto had been part of the familiar picture of the solar system for generations, but scientifically the reclassification reflected a deeper understanding. Pluto was not an isolated outer planet. It was part of a vast population of distant objects, the Kuiper Belt, a region that extends far beyond Neptune. Thinking about Pluto today means thinking about that broader context. It is one of many worlds at the edge of the familiar, a region where distances are so great and sunlight so faint that the solar system begins to feel less like a collection of planets and more like a wide, scattered frontier. When the New Horizons spacecraft approached Pluto in 2015, it transformed our understanding of this distant world. Before the flyby, Pluto was little more than a blurry disk in the best telescopes. Afterward, it became a landscape, a place with mountains, plains, and an atmosphere. One of the most striking features discovered was a vast heart-shaped region known as Sputnik Planitia, a basin filled with nitrogen ice that appears to be slowly flowing, reshaping the surface over time. The presence of such active geology was unexpected. At such low temperatures, far from the Sun, many scientists had assumed Pluto would be geologically dead, frozen and unchanging. Instead, it turned out to be a dynamic world, reminding us that distance from the Sun does not necessarily mean inactivity. Mountains of water ice rise several kilometers above the plains, their surfaces rugged and sharp. The atmosphere, though extremely thin, changes with the seasons, freezing onto the surface when Pluto moves farther from the Sun and sublimating back into gas when it comes closer. These discoveries revealed something important about the outer solar system. Even small worlds, even those billions of kilometers away, can be complex and evolving places. But Pluto is only one of many such worlds. Eris, as mentioned earlier, orbits at an average distance of about 68 astronomical units, much farther than Pluto. Its surface is thought to be coated with frozen methane and nitrogen, reflecting sunlight so efficiently that it appears bright despite its enormous distance. Haumea, another dwarf planet, is unusual in a different way. It rotates so rapidly that it has been stretched into an elongated shape, more like a flattened ellipsoid than a sphere. It is also surrounded by a family of smaller objects, fragments thought to have formed from a collision long ago. Makemake, yet another dwarf planet, lies in a distant orbit and has a surface rich in methane ice, giving it a reddish appearance in telescopic images. And beyond these named worlds are countless smaller objects, many still unnamed, many still undiscovered, drifting in the cold darkness beyond Neptune. The distances between these objects are immense. Even though they belong to the same general region, the Kuiper Belt, they are separated by millions or even hundreds of millions of kilometers. A spacecraft traveling between them would spend years crossing empty space, with nothing visible but distant points of light. That emptiness is part of what defines this region. It is not a crowded field of debris, but a vast expanse where objects are scattered thinly across enormous distances. The Sun, seen from Pluto, appears about 1,000 times fainter than it does from Earth. It still shines, still casts shadows, but the light is pale and distant, more like a brilliant star than the blazing disk we see in our sky. Temperatures there are extremely low, often below -220 degrees Celsius. Ices that would vaporize instantly on Earth remain solid, forming landscapes of frozen nitrogen, methane, and carbon monoxide. And yet, even at such distances, the Sun's gravity still holds these worlds in orbit. They remain part of the solar system, bound to the same star that warms Earth and drives the weather of our planet. That realization can be difficult to absorb. The solar system extends not just to the orbit of Neptune, not just to Pluto, but far beyond, into regions where objects take centuries or even millennia to complete a single orbit around the Sun. Pluto itself takes about 248 Earth years to circle the Sun once. That means it has not yet completed a full orbit since its discovery in 1930. It is still moving along the same long path, slowly tracing its course through the outer solar system. There is something quietly humbling about that timescale. Civilizations rise and fall on Earth while Pluto moves only a small fraction of its orbit. The dwarf planets of the Kuiper Belt mark a kind of threshold, the edge of what feels familiar. Beyond them, objects become smaller, more distant and harder to detect. The solar system continues, but it becomes increasingly diffuse, increasingly difficult to map. And yet, even here, we are still not near the true boundary of the Sun's influence. If you continue travelling outward past Pluto and the scattered dwarf worlds, something subtle begins to change. The solar system no longer feels defined by planets, or even by icy bodies drifting in distant orbits. Instead, the environment itself begins to shift. The space around you is still mostly empty, still dark, still cold, but it is no longer shaped only by gravity and distant sunlight. There is another influence at work, one that extends far beyond the orbits of the planets, far beyond the Kuiper Belt, reaching into a region where the Sun's presence is no longer visible in any familiar way. That influence is the solar wind. The Sun is not just a glowing sphere of light and heat. It is also constantly releasing a stream of charged particles, mostly electrons and protons, flowing outward in all directions at speeds of hundreds of kilometers per second. This outflow is called the solar wind, and although it is extremely thin, far more rarefied than any vacuum we can create on Earth, it fills the entire solar system. Near Earth, the solar wind is almost imperceptible. Our planet's magnetic field deflects most of these particles, creating the protective bubble known as the magnetosphere. Occasionally, some of the particles follow magnetic field lines into the upper atmosphere, producing the auroras, those shimmering curtains of green and red light that ripple across polar skies. But the solar wind does not stop at Earth. It continues outward, past Mars, past Jupiter, past Saturn and Neptune, expanding in all directions like an invisible tide moving through space. Eventually, however, it encounters something else: the thin gas and magnetic fields that exist between the stars. Interstellar space is not completely empty. It contains traces of hydrogen atoms, stray ions, and the faint influence of the galaxy's magnetic field. When the solar wind pushes against this interstellar medium, it begins to slow down, compress, and change. The region carved out by the solar wind, this enormous bubble surrounding the Sun, is called the heliosphere. Understanding the heliosphere is essential if we want to understand how big the solar system really is, because in one sense, this bubble marks the farthest reach of the Sun's direct physical influence. Beyond it, space is no longer dominated by particles from our star, but by the environment of the galaxy itself. The heliosphere is vast beyond ordinary imagination. Its boundary lies roughly 120 astronomical units from the Sun in the direction that spacecraft have measured, though its shape is not perfectly spherical. Because the solar system is moving through interstellar space, the heliosphere is slightly compressed in the direction of motion and stretched out behind, rather like the wake trailing behind a boat moving through water. If you were travelling outward, you would not encounter this boundary as a sharp wall. Instead, the transition would be gradual. First, you would cross a region called the termination shock. Here, the solar wind slows from supersonic speeds to subsonic speeds as it begins to feel the pressure of the interstellar medium. The change is not dramatic to the eye, because there is little to see, but instruments would detect a shift in particle energies and magnetic fields. Farther out lies the heliosheath, a vast, turbulent region where the slowed solar wind piles up, swirling and mixing as it presses outward against interstellar space. This region is enormous, tens of astronomical units thick, a kind of borderland where the Sun's influence fades gradually rather than abruptly. And then at last comes the heliopause, the outer boundary of the heliosphere. This is the point where the pressure of the solar wind balances with the pressure of interstellar space. Beyond this boundary, the particles surrounding you no longer originate primarily from the Sun. Crossing the heliopause means entering interstellar space. It may sound like a dramatic moment, but in reality, it is quiet and subtle. There is no flash of light, no sudden darkness, no visible line marking the transition. Only instruments can detect the change. A drop in solar particles, a rise in cosmic rays from distant stars, a shift in magnetic fields. And yet, scientifically, it is one of the most significant boundaries in our cosmic neighbourhood. For decades, the heliosphere was only a theoretical concept, something predicted by models but not directly observed at its edge. Then, in the early 21st century, humanity achieved something extraordinary. The Voyager spacecraft, launched in 1977, travelling faster and farther than any human-made objects before them, began to approach this distant frontier. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018. These spacecraft are now in interstellar space, still sending back faint signals, still carrying instruments that measure the environment far beyond the planets. It is remarkable to think about those signals. Radio waves travelling billions of kilometres, taking more than 20 hours to reach Earth, carrying information from regions of space no human has ever seen directly. The Voyagers are still moving outward, slowly but steadily, each second carrying them farther from the Sun, deeper into the galaxy. Long after their instruments fall silent, they will continue drifting, silent messengers from a distant star system. Thinking about the heliosphere also helps us understand something about the Sun itself. Stars are not isolated objects. Each one interacts with its surroundings, shaping the space around it with winds, radiation, and magnetic fields. Our heliosphere is just one example of this process, a bubble carved into the interstellar medium by the steady flow of particles from our star. Other stars likely have their own astrospheres, similar bubbles of influence surrounding them, though we cannot observe most of them directly. In that sense, the heliosphere is both unique and universal, a feature of our solar system that reflects a broader pattern throughout the galaxy. There is also something quietly reassuring about the heliosphere, because it serves as a kind of shield. This solar wind helps deflect some of the high-energy cosmic rays that travel through interstellar space, reducing the amount of radiation that reaches the inner solar system. Without this protective bubble, conditions near Earth might be very different, perhaps less hospitable to life. The heliosphere, then, is not just a boundary, it is part of what makes our environment what it is, and yet even this enormous bubble is not the outermost extent of the solar system in every sense. Gravity reaches farther than the solar wind. The sun's gravitational influence extends far beyond the heliopause, holding distant icy bodies in orbits that may take millions of years to complete. This is an important distinction. The heliosphere marks the boundary of the sun's particle influence, but not necessarily the boundary of its gravitational domain. If you imagine the solar system as a kind of territory, the heliosphere is like the edge of the atmosphere, where the air thins and the sky turns black. But gravity continues to act beyond that point, binding distant objects in slow, distant orbits. And that brings us to a question that astronomers still explore. How far does the sun's gravity really extend? Where is the true outer edge of the solar system, if such a thing can be defined at all? The answer may lie in a region so distant that no spacecraft has ever reached it, a vast cloud of icy bodies that surrounds the solar system at distances tens of thousands of times greater than Earth's orbit. But before we turn to that distant frontier, it is worth lingering for a moment on the idea of the heliosphere itself, because it changes how we think about size in a subtle way. Until now, much of our discussion has focused on objects, planets, moons, asteroids, dwarf planets. These are tangible things, places with surfaces and orbits, worlds that can be mapped and photographed. The heliosphere is different. It is not a solid object, not even a collection of objects, but a region defined by motion and energy, by streams of particles moving through space. It is invisible to the eye, yet enormous in scale, far larger than the region occupied by the planets. This reminds us that the solar system is not just a collection of worlds. It is also an environment shaped by forces and fields that extend far beyond anything we can see directly. If you were drifting somewhere near the heliopause, far beyond Pluto, the sun would appear as an extremely bright star, far brighter than any other, but still just a point of light. The nearest planets would be impossibly distant, lost in the glare near the sun. The sky would be filled with stars, sharp and steady, unblinking in the darkness. And around you, though invisible, would be the boundary between two different cosmic environments, the realm shaped by our star and the vast interstellar medium beyond. That realization carries a certain quiet weight. It reminds us that the solar system is not an isolated island, but a region embedded within a much larger galaxy, moving through space surrounded by other stars, other systems, other bubbles carved by distant suns. Long before anyone expected a human-made object to travel beyond the planets, two small spacecraft were launched from Earth with a very specific purpose. They were not originally intended to leave the solar system at all. Their mission was to take advantage of a rare planetary alignment, a configuration that happens only about once every 176 years, in which the giant planets line up in a way that allows a spacecraft to visit several of them in sequence, using each planet's gravity to gain speed and redirect its path. These spacecraft were Voyager 1 and Voyager 2, launched in 1977, only weeks apart. At the time, their planned journeys were ambitious enough: fly past Jupiter and Saturn, study their moons and rings, and send back images and data that would transform our understanding of the outer planets. No one could be entirely sure what would happen after that. The spacecraft would keep moving, of course, but how far they might go and what they might encounter was still uncertain. To appreciate what Voyager accomplished, it helps to imagine the scale of the journey from the beginning. When Voyager 1 lifted off from Earth, it began as all spacecraft do, climbing through the atmosphere, circling the planet, and then accelerating outward. In those early hours, it was still close to home, still within the region dominated by Earth's gravity. Soon after, it escaped Earth's pull and entered orbit around the Sun, beginning the long arc outward toward Jupiter. The trip to Jupiter alone took nearly 2 years. That distance, which now feels modest compared to where Voyager is today, was at the time an enormous step outward, farther than any spacecraft had travelled before, while still remaining operational and under close observation. When Voyager 1 arrived at Jupiter in 1979, it revealed a world more dynamic than anyone had expected. Active volcanoes were discovered on the moon Io, erupting continuously, driven by the immense tidal forces exerted by Jupiter's gravity. Europa's smooth, icy surface hinted at a hidden ocean beneath. The intricate structure of Jupiter's rings and the complexity of its atmosphere became clearer than ever before. After its encounter with Jupiter, Voyager 1 used the planet's gravity to change its trajectory, accelerating and heading towards Saturn. This technique, called a gravity assist, works by borrowing a tiny amount of a planet's orbital energy. The spacecraft falls toward the planet, swings around it, and departs at a higher speed, redirected along a new path. Saturn was reached in 1980. There, Voyager revealed extraordinary details about the rings, showing them to be far more complex and structured than previously imagined. The moon Titan, shrouded in a thick atmosphere, drew particular interest. Because Titan was such an intriguing target, Voyager 1's trajectory was adjusted to pass close to it, and that decision had a consequence. After Saturn, Voyager 1 would no longer be aligned to visit Uranus or Neptune. Instead, it was flung upward, out of the plane of the planets, beginning a journey that would eventually carry it toward interstellar space. Voyager 2 followed a different path. After Jupiter and Saturn, it continued onward to Uranus, arriving in 1986 and then to Neptune in 1989, becoming the only spacecraft ever to visit those distant worlds. With that final planetary encounter, Voyager 2, like its twin, was set on a course that would carry it beyond the known planetary region of the solar system. From that point forward, the Voyagers were no longer explorers of planets. They became explorers of distance itself. Both spacecraft continued outward, moving through regions of space where the sun's warmth is faint, where the planets are far behind, and where the environment is shaped less by visible objects and more by invisible forces. Their instruments, designed to measure magnetic fields, charged particles, and cosmic rays, began to study the outer reaches of the heliosphere. It is difficult to grasp just how far they have travelled. Voyager 1 is now more than 160 astronomical units from the Sun. That means it is more than 160 times farther from the Sun than Earth is. Light, travelling at nearly 300,000 kilometers per second, takes over 20 hours to make the round trip between Earth and Voyager 1. Imagine sending a message and waiting nearly a full day to hear the reply. That delay is part of the daily reality of communicating with spacecraft at such distances. Another remarkable aspect of the Voyagers is their longevity. Designed for missions expected to last only a few years, they have continued operating for decades, powered by radioisotope thermoelectric generators that convert heat from the decay of plutonium into electricity. Over time, their power output has slowly declined, and engineers have had to shut down some instruments to conserve energy, but the spacecraft continue to function, still sending back data from regions no human-made object had ever reached before. In 2012, Voyager 1 crossed the heliopause, becoming the first spacecraft to enter interstellar space. Voyager 2 followed in 2018. These crossings were not marked by dramatic visual changes, but by subtle shifts in the data. A drop in particles from the solar wind, an increase in cosmic rays from beyond the solar system, and changes in the magnetic field. For the first time, humanity had instruments operating in the space between the stars. there is something quietly profound about that fact. The Voyagers carry no crew, no ability to return, no means of repair. They move steadily outward, year after year, following trajectories set in motion decades ago, each second carrying them farther from the Sun. And yet, despite their distance, they remain connected to Earth by a faint stream of radio signals, detected by enormous antennas of the Deep Space Network. These antennas must be precisely aimed, because the signals arriving from Voyager are incredibly weak, comparable to the power of a small household appliance spread across billions of kilometers. That connection, fragile as it is, links our world to the farthest reaches of the solar system. The Voyagers also carry something symbolic, a message intended not for us, but for whoever or whatever might one day encounter them. Each spacecraft contains a golden record, a phonograph disc plated in gold, along with a stylus and instructions for playback. The record contains sounds and images from Earth, greetings in many languages, music from different cultures, the sounds of wind and rain, of footsteps and laughter. It also contains a map showing the position of the Sun relative to nearby pulsars, a kind of cosmic address, in case anyone should ever find the spacecraft and wonder where they came from. The chances of that happening are extremely small. Space is vast beyond imagination, and the Voyagers are tiny objects moving through it, but the records were included as a gesture, a quiet statement that humanity, having reached beyond its own world, chose to carry with it a trace of who we are. Thinking about the Voyagers changes how you think about the size of the solar system. Before them, the outer regions were largely theoretical, understood through observation and calculation but not through direct measurement. The Voyagers turned those distant regions into places we have visited, places from which we have received data. And yet, even after travelling for nearly half a century, the Voyagers have not reached the true outer limits of the Sun's gravitational influence. They are only beginning to pass through the outermost regions of the heliosphere and into interstellar space, still far from the distant Oort Cloud, which may extend tens of thousands of astronomical units from the Sun. At their current speed, it would take Voyager tens of thousands of years to reach the inner edge of that distant cloud, and far longer to pass through it entirely. That perspective is humbling. The spacecraft that represent the farthest reach of human exploration have only begun to leave the solar system in the broadest sense. The true outer regions remain unimaginably distant. Another way to understand the scale is to think about time. Voyager 1 travels at about 17 kilometers per second relative to the Sun. That is incredibly fast by human standards. A jet aircraft moves at less than 1/10 of that speed. A rifle bullet travels at less than 1/20th. And yet, even at that speed, crossing the solar system takes decades. Distance in space is so vast that even our fastest machines require lifetimes to traverse it. There is also something quietly moving about the fact that the Voyagers are now the most distant human artifact ever created. Every human being who has ever lived remains far behind them, on a small planet orbiting a distant star. The spacecraft carry with them traces of our knowledge, our curiosity and our desire to explore. Long after their instruments fall silent, after their power is exhausted and their transmitters go quiet, the Voyagers will continue drifting. They will orbit the centre of the Milky Way along with the Sun, taking hundreds of millions of years to complete a single galactic orbit. In that sense, they have already begun journeys far longer than any human civilization has yet endured. Imagining their path can be strangely calming. Two small objects moving steadily through darkness, guided only by the laws of physics, carrying with them a silent record of a distant world. There is no urgency in their motion, no deadlines, no schedules, only steady movement second by second, year after year, and their journey helps answer a deeper question about the size of the solar system, because it shows that the boundary of our cosmic neighbourhood is not a simple line, not a place you reach in a day or even a decade, but a vast and gradual transition extending far beyond the planets. The Voyagers remind us that the solar system is not just the region of planets we learned about in school. It is a much larger environment, one that stretches outward for distances so great that even our farthest spacecraft are only beginning to explore it. Far beyond the path of Neptune, beyond the scattered dwarf planets, and even beyond the invisible boundary of the heliosphere, there is a region that stretches the imagination almost to its limit. Unlike the planets, or even the Kuiper Belt, this region has never been directly observed. No spacecraft has reached it, no telescope has imaged it clearly, and yet astronomers are almost certain it exists. This distant region is known as the Oort Cloud. To understand why scientists believe in something so remote, it helps to think about comets. For centuries, comets were mysterious visitors, appearing suddenly in the sky with long, glowing tails, then fading and disappearing again. Some returned regularly, like Halley's Comet, which comes back roughly every 76 years. Others appeared only once, following paths that carried them far out of the solar system, perhaps never to return. When astronomers began calculating the orbits of these long-period comets, they noticed something remarkable. Many of them seemed to arrive from extremely distant regions, approaching the Sun from all directions, not just from the flat plane where the planets orbit. Their trajectories suggested a source not in a disk like the Kuiper Belt, but in a vast, roughly spherical distribution surrounding the solar system. In 1950, the Dutch astronomer Jan Oort proposed an explanation. He suggested that the solar system is surrounded by a distant cloud of icy bodies, remnants from the formation of the planets, orbiting at distances tens of thousands of astronomical units from the Sun. Occasionally, passing stars or gravitational disturbances would nudge some of these objects inward, sending them toward the Sun as long-period comets. This idea fit the observations remarkably well, and over time it became widely accepted, even though the Oort cloud itself remains too distant and too faint to observe directly. The scale of the Oort cloud is difficult to grasp. While the Kyper Belt extends to perhaps 50 astronomical units, the inner edge of the Oort cloud may begin thousands of astronomical units from the Sun, and the outer edge could lie as far as 50,000 to 100,000 astronomical units away. To put that into perspective, one astronomical unit is the distance from Earth to the Sun. At 100,000 astronomical units, you're nearly halfway to the nearest stars. Light, which takes only 8 minutes to travel from the Sun to Earth, would take more than a year to cross the diameter of the inner Oort cloud and many years to cross its outer reaches. At such distances, the Sun would no longer appear as a bright disk or even a brilliant star. It would be just another point of light in the sky, brighter than most stars but not overwhelmingly so. And yet, even there, its gravity still holds sway, binding these distant icy bodies in slow, elongated orbits that may take millions of years to complete. Imagining the Oort cloud requires a different way of thinking about the solar system. Up to this point, we have been picturing a relatively flat system, a disk of planets orbiting in roughly the same plane. The Oort cloud, by contrast, is thought to be spherical, surrounding the solar system in all directions like a vast halo. If the planetary region were the size of a coin, the Oort cloud would extend out to the size of a city. Within that enormous volume, the objects themselves are tiny and widely separated. There may be trillions of icy bodies in the Oort cloud, but the distances between them are so great that a spacecraft travelling through it might pass for years without encountering anything larger than a speck of ice. It would feel less like flying through a cloud and more like drifting through a vast, dark ocean with occasional distant grains of dust. Temperatures in the Oort cloud are extremely low, only a few degrees above absolute zero. Sunlight is faint, barely distinguishable from the glow of distant stars. The environment is quiet beyond any human experience, with no nearby planets, no significant radiation from the Sun, and only the slow drift of distant icy bodies moving along their immense orbits. And yet, this region is still part of the solar system. That is one of the most surprising aspects of the Oort Cloud. The solar system is not just the region of planets, or even the region of the heliosphere. It may extend tens of thousands of times farther than the distance from Earth to the Sun, forming a gravitational domain that reaches deep into interstellar space. The boundary between the solar system and the galaxy is not a sharp line. It is a gradual transition, where the Sun's gravitational influence weakens until the gravitational pull of other stars and the tides of the Milky Way begin to dominate. At the outer edge of the Oort Cloud, an object might be only loosely bound to the Sun, easily perturbed by passing stars or molecular clouds drifting through the galaxy. Over millions of years, some of these objects may be stripped away entirely, becoming free-floating bodies wandering the interstellar medium. Others may be nudged inward, beginning long journeys that eventually bring them into the inner solar system as comets, glowing briefly in the sunlight before retreating once more into the darkness. That slow exchange of material between the solar system and the galaxy is part of what makes the Oort Cloud so fascinating. It is not just a boundary, but a dynamic region, shaped by the gravitational influence of nearby stars, by the motion of the Sun through the Milky Way, and by events that unfold over timescales far longer than human history. Thinking about those timescales can be strangely calming. An object in the outer Oort Cloud might take millions of years to complete a single orbit around the Sun. Entire ice ages on Earth would pass while that distant body moved only a small fraction of its path. Civilizations would rise and fall, continents would shift, species would evolve, and still, the distant comet would continue its slow journey through the darkness. The Oort Cloud also reminds us that the solar system is not isolated. The Sun is one of hundreds of billions of stars in the Milky Way, and as it orbits the galactic center, it passes through regions of varying density, sometimes closer to other stars, sometimes farther away. Over billions of years, these encounters have likely shaped the structure of the Oort Cloud, stirring it, reshaping it, perhaps even capturing or losing objects along the way. In that sense, the outermost solar system is not a fixed, unchanging structure, but part of a larger galactic environment, influenced by forces far beyond the reach of any spacecraft. And yet, despite its distance and mystery, the Oort Cloud plays a role in our own experience of the night sky. Many of the bright comets that have fascinated observers throughout history, comets that appeared suddenly and dramatically, may have originated in this distant reservoir. When we see a comet blazing in the sky, with its glowing tail stretching across the stars, we may be witnessing an object that has spent most of its existence tens of thousands of astronomical units from the Sun, travelling for millions of years before making a brief visit to the inner solar system. There is something quietly extraordinary about that thought, that a fragment of ice formed in the earliest days of the solar system can journey across such immense distances and become visible to human eyes, if only for a short time. The Oort Cloud, then, represents a kind of frontier, not a sharp edge, but a vast and diffuse boundary where the solar system gradually fades into the wider galaxy. It is likely that no spacecraft will reach it for many centuries, perhaps millennia given current technology. The distances are simply too great. Even Voyager, moving faster than any other human-made object, would take tens of thousands of years to reach the inner edge of the Oort Cloud and far longer to cross it entirely. And yet, knowing that this distant region exists changes how we think about the size of our cosmic neighbourhood. The solar system is not a small collection of planets orbiting a star. It is a vast domain, stretching far beyond the limits of direct observation, extending into regions so distant that the Sun itself becomes just another star in the sky. At this point, after travelling outward in our minds from Earth to the Moon, past the planets, through the Kuiper Belt, and all the way to the distant reaches of the heliosphere and the imagined boundary of the Oort Cloud, the numbers involved have grown so large that they begin to lose their meaning. Tens of millions of kilometres, billions of kilometres, tens of thousands of astronomical units. These figures are precise, But precision alone does not always help us feel the scale of something, so it can be helpful to do something different for a moment. Instead of trying to stretch our minds to match the solar system, we can shrink the solar system down to match our minds. We can imagine it as a map, or a model, or a landscape small enough to walk through. Something that translates cosmic distances into steps, meters, and familiar spaces. This approach doesn't change the proportions. The planets remain just as small compared to the distances between them. But when everything is scaled down together, the relationships become easier to grasp, and the vastness begins to feel more real. Let's start with a simple example. Imagine placing the sun on a large open field and shrinking it to the size of a basketball. A basketball is about 24 centimeters across, easy to picture, easy to hold. Now imagine that everything else in the solar system shrinks by the same proportion. At that scale, Earth would be about the size of a small pea, roughly 2 millimeters across, and the distance between the basketball sun and that tiny pea Earth would not be a few steps. It would be about 26 meters, roughly the length of a modest swimming pool. Already that feels different from the diagrams we usually see. The sun and Earth are not close together at all. There is a wide stretch of empty space between them, space you would have to walk across to reach the tiny speck that represents our world. Now imagine continuing outward. Mars, even smaller than Earth in this model, would lie about 40 meters from the basketball sun. Jupiter, which in reality is enormous compared to Earth, would still only be about the size of a grape, but it would sit more than 130 meters away. Saturn, slightly smaller, would be around 240 meters out, nearly a quarter of a kilometer from the center. Uranus and Neptune would lie even farther, several hundred meters away, tiny spheres in the distance, barely noticeable unless you knew exactly where to look. And Pluto, if included in this model, would be nearly a kilometer away from the sun, smaller than a grain of sand. What becomes striking when you imagine this is not just how small the planets are, but how far apart they are. Walking from the basketball sun to Neptune would take several minutes, and most of that walk would be spent crossing empty space, seeing nothing but distant markers on the horizon. That emptiness is not an exaggeration. It is one of the defining features of the solar system. Another way to think about scale is to imagine compressing the solar system into something the size of a city. Suppose the sun were placed at the centre of a large urban park. Mercury might be a tiny bead only a few dozen meters away. Earth would be a small dot a few hundred meters out. Jupiter might lie several kilometers from the centre, and Neptune perhaps 10 kilometers or more. At that scale, the Kuiper Belt would stretch beyond the edges of the city, and the Oort Cloud would extend far beyond, perhaps as far as neighbouring towns, or even across an entire region. In that version of the solar system, most of the space between worlds would feel like long stretches of highway, farmland, or open countryside. The planets themselves would be tiny landmarks scattered across enormous distances. These kinds of models help reveal something important. When we look at textbook diagrams, the planets often appear crowded together because the page cannot accommodate the true distances. If drawn accurately, the planets would be so far apart that the page would be mostly blank. The solar system, in reality, is mostly blank. There are also real-world models built at this kind of scale. In several places around the world, educators have created walking-scale solar system trails, where each step corresponds to millions of kilometers. Visitors begin at a large representation of the Sun, then walk for some distance before reaching Mercury, then farther to Venus, then farther still to Earth. What people often notice is how quickly the distances grow. The first few planets appear relatively close together, but as the walk continues, the gaps become larger and larger. By the time they reach Jupiter or Saturn, the earlier planets feel clustered near the starting point, and the outer markers are spread widely across the landscape. And if the model includes Pluto or the Kuiper Belt, those markers may be placed far beyond the others, sometimes at the edge of the trail or even beyond it, emphasizing just how large the solar system really is. There is something quietly effective about walking such a model. Each step takes time. Each stretch of empty ground becomes part of the experience. You begin to feel, rather than just calculate, the vastness involved. Another useful way to shrink the solar system into something relatable is to think in terms of travel times, but scaled to human speeds. Imagine you could walk at a steady pace of 5 kilometers per hour through our basketball-sized solar system. Walking from the Sun to Earth, about 26 meters in this model, would take only a few seconds. But walking out to Jupiter, more than 130 meters away, would take nearly half a minute. Walking to Neptune, several hundred meters distant, would take a few minutes. That may not sound dramatic, but remember that the planets themselves are tiny. Most of the time would be spent crossing empty ground with nothing to see but distant markers. Now imagine extending this model to include the inner edge of the Oort Cloud. At the same scale, that boundary might lie tens of kilometers away, far beyond walking distance in a casual stroll, more like a long journey across a region than a walk in a park. And the outer edge might be hundreds of kilometers away, farther than many people travel in a day. This comparison helps show just how large the solar system truly is. The planetary region, from Mercury to Neptune, occupies only a small inner portion of the Sun's domain. Beyond it lies a vast frontier that stretches far into interstellar space. There is also something interesting about how shrinking the solar system changes our sense of the planets themselves. Jupiter, which feels enormous in astronomical discussions, becomes a grape in the basketball model. Earth becomes a tiny speck. The Sun, though still large compared to the planets, becomes something you could hold in your hands. That shift in perspective can be strangely grounding. It reminds us that size is always relative. The Sun is enormous compared to Earth, but small compared to many stars. Earth is large compared to a person, but tiny compared to Jupiter. And all of them together are small compared to the vastness of the solar system. Another approach is to imagine the solar system scaled to time rather than distance. Suppose the distance from the Sun to Neptune were represented by a single day's walk from sunrise to sunset. Earth would lie only a short time after dawn, Jupiter perhaps around midday, and Neptune near evening. The Oort Cloud would extend far into the night, long after the sun had set. In that sense, most of the solar system exists in the darkness beyond the familiar daylight of the planets. This kind of thinking also helps explain why exploration takes so long. Spacecraft, even moving at extraordinary speeds, still require years to cross the distances between planets. Voyager has been travelling for nearly half a century and is still within the broader gravitational domain of the Sun. If the solar system were a map you could unfold on a table, the planets would be tiny dots separated by vast blank areas. Most of the map would be empty, not because nothing exists there, but because space itself is so immense. And that emptiness is not just a curiosity. It has real consequences. It shapes how spacecraft travel, how signals are transmitted, how gravity acts, and how rare collisions between objects are. It also shapes our understanding of how planetary systems form, because the distances between bodies influence how they interact over billions of years. There is another quiet realization that comes from imagining the solar system as a map. Our entire human history, every city, every ocean crossing, every journey ever made, has taken place on a speck no larger than a grain of sand in that model. All of our concerns, ambitions and stories exist within a tiny fraction of the solar system's extent. And yet, from that small beginning, we have sent machines across billions of kilometers, measured distances to distant stars, and begun to understand the structure of our cosmic neighborhood. That ability to comprehend something so vast, even imperfectly, is one of the remarkable achievements of human curiosity. Once you begin to think about the solar system as a map, with planets reduced to tiny markers and distances stretched across fields or cities, one idea begins to stand out more than any other. It is not the size of the planets that defines the solar system, it is the emptiness between them. That emptiness is easy to overlook at first. When we see images of space in books or films, the scenes are often filled with glowing clouds, bright stars, or clusters of asteroids drifting close together. These images can be beautiful, but they give a misleading impression. Most of the solar system does not look like that at all. Most of it is quiet, dark, and nearly empty, with distances so large that even the nearest objects are separated by vast stretches of nothing. To understand this properly, it helps to think again about the scaled models we imagined earlier. In the basketball-sized solar system, the planets were tiny and widely spaced, and most of the journey between them was spent crossing open ground. Now imagine that same model at night, in a wide field, with only a few faint markers visible in the distance. That is closer to what space really feels like. Even in the asteroid belt, which many people picture as crowded, the distances between large objects are enormous. A spacecraft can travel through that region without encountering any nearby rocks at all, unless it deliberately aims for one. The asteroids are scattered across millions of kilometers, each following its own orbit, rarely coming close to another. The same is true in the Kuiper Belt, and even more so in the regions beyond. Objects are separated by such immense distances that collisions are rare on human timescales. Most of the time, space is simply empty. But what does empty actually mean? It does not mean absolute nothingness. Even in the emptiest regions of interplanetary space, there are still particles, atoms of hydrogen, stray dust grains, and streams of charged particles from the solar wind. But these are incredibly sparse. Near Earth's orbit, there may be only a few particles per cubic centimetre, far fewer than in any vacuum we can produce in a laboratory. Farther from the Sun, the density drops even more. In the outer solar system, space becomes so thin that the particles are separated by distances measured in centimetres or metres. It is an emptiness beyond ordinary experience, quieter and more complete than anything we encounter on Earth. Sound cannot travel there, because there is no air or water to carry vibrations. A spacecraft moving through space does so in complete silence, hearing only the faint hum of its own systems. There is also very little resistance. On Earth, moving objects are constantly slowed by friction with the air or ground. In space, once a spacecraft is set in motion, it continues moving unless acted upon by gravity or by firing its engines. This is why spacecraft can coast for years, drifting along trajectories determined long ago. That quiet, frictionless motion is one of the defining characteristics of space. It is a place where motion persists, where objects follow their paths without interruption, where the laws of physics unfold in their simplest form. Another way to grasp the emptiness is to think about visibility. If you were floating in interplanetary space, far from any planet, the sky would not look crowded or dramatic. The sun would shine as a bright disk, and the stars would appear sharp and steady, but most of the time, you would see nothing else. Even large planets are difficult to see from a distance. Jupiter, enormous as it is, would appear as a bright point until you were relatively close. The smaller planets would be invisible to the naked eye at most distances. This means that a traveller moving between worlds would spend most of the journey with no visible destination, navigating by instruments and calculations rather than by sight. The destination would remain a faint point of light until the final stages of the approach. That experience has been described by astronauts and mission planners alike. Space travel is not a constant parade of scenery. It is long periods of quiet motion punctuated by brief moments of arrival. The emptiness also affects temperature in ways that may seem surprising. Space is often described as cold, and in many ways it is, but not because it is filled with cold air. Instead, objects in space lose heat slowly by radiation, and they gain heat only from sunlight or internal sources. A spacecraft in sunlight can become quite warm, while one in shadow can become extremely cold. The temperature depends on exposure to radiation, not on the surrounding environment, because there is almost no surrounding environment to exchange heat with. This lack of atmosphere also means there is no scattering of light. On Earth, the sky appears blue because sunlight is scattered by air molecules. In space, the sky is black, even when the sun is shining, because there is nothing to scatter the light. That blackness is another aspect of the emptiness, a visual reminder that space is not filled with glowing air or haze. It is a near-perfect vacuum, illuminated only by distant stars and the occasional reflection from a nearby object. There is also a psychological dimension to this quiet vastness. Human beings are used to environments filled with sound, motion and activity. Even in the most remote deserts or oceans, there is wind, water, or the rustle of life. Space offers none of that. It is silent and still on a scale that can be difficult to imagine, and yet there is something calming about that stillness when you think about it gently. The solar system is not chaotic or crowded. It is spacious, orderly, and slow-moving, with worlds tracing their paths in silence, separated by distances that ensure they rarely disturb one another. That spaciousness is one of the reasons planetary systems can remain stable for billions of years. If the planets were much closer together, their gravitational interactions would be stronger and more disruptive. The wide gaps between orbits help maintain stability, allowing worlds to follow predictable paths over immense spans of time. Another way to appreciate the emptiness is to think about how small spacecraft appear in comparison. Voyager, now billions of kilometers from Earth, is moving through a region so vast that even if another spacecraft were nearby, they might never see each other. The distances are simply too large, the volumes of space too immense. Communication across these distances also highlights the scale. Signals take minutes or hours to travel between Earth and distant probes, and those signals spread out as they travel, becoming incredibly faint. Detecting them requires enormous antennas and precise calculations. All of this reinforces the same idea. Space is not just big, it is mostly empty. And that emptiness continues even beyond the planetary region, beyond the Kuiper Belt, beyond the heliosphere, and into the distant reaches of the Oort Cloud. The solar system in its fullest sense is not a crowded collection of worlds, but a vast domain where matter is sparse and distances are immense. There is something quietly humbling about that realization. The planets, impressive as they are, occupy only a tiny fraction of the volume of the solar system. Most of it is silent space, stretching outward in every direction, gradually blending into the interstellar medium. Understanding that helps answer a deeper question about size. When we ask how big the solar system is, we're really asking how far the sun's influence extends across that quiet emptiness. And that leads naturally to the next question, one that is not as simple as it first appears. Where does the solar system actually end? And at what point do we begin to say that we are no longer in our own cosmic neighbourhood, but in the vast space between the stars? It feels like there should be a clear answer, a boundary you could draw on a diagram, a line marking the transition from our cosmic neighbourhood to the wider galaxy beyond. But the more closely astronomers study this question, the more they realise that the solar system does not have a single, obvious edge. Instead, it fades outward gradually, and what counts as the end depends on what you mean. One way to think about it is in terms of gravity. The sun's gravity reaches infinitely far in principle, weakening with distance but never truly disappearing. Every object in the solar system, from the closest asteroid to the farthest comet in the distant Oort Cloud, is held in orbit by that gravitational pull. Even objects thousands or tens of thousands of astronomical units away are still, in a sense, part of the sun's domain. If we define the solar system this way, then its outer boundary might lie at the farthest distance where objects remain gravitationally bound to the sun. That would place the edge somewhere in the outer Oort Cloud, perhaps 50,000 or even 100,000 astronomical units from the sun. At those distances, the gravitational pull of nearby stars and the tidal forces of the Milky Way begin to compete with the sun's influence. Objects can be nudged out of orbit, stripped away or perturbed onto long journeys inward. But gravity is only one way to define a boundary. Another way is to think about the environment of space itself. Inside the heliosphere, the solar wind dominates. Charged particles streaming outward from the sun fill the region, shaping the magnetic environment and helping shield the inner solar system from some cosmic radiation. Outside the heliosphere, the situation changes. The solar wind fades, and the particles surrounding you come primarily from interstellar space. This boundary, the heliopause, is often considered the place where interstellar space truly begins, at least in terms of the local environment. When Voyager 1 crossed the heliopause in 2012, it entered a region where the density and energy of cosmic rays increased and the solar wind diminished sharply. It was the first time a human-made object had reached that frontier, and yet even beyond the heliopause, the sun's gravity still holds sway. The spacecraft are still orbiting the galaxy along with the sun, still moving within the broader gravitational domain of our star, so in that sense they have not completely left the solar system, depending on how you define it. This ambiguity reveals something important. The solar system is not like a country with a clearly marked border. It is more like a fading glow, gradually diminishing until it becomes indistinguishable from the background of the galaxy. If you were travelling outward, you would not encounter a sudden change, no sharp line where one region ends and another begins. Instead, you would notice subtle shifts. The solar wind would weaken, cosmic rays would become more common. The sun would grow fainter in the sky, eventually appearing as just another bright star among many. At some point, the sun would no longer dominate your surroundings. It would still be visible, still brighter than most stars, but it would no longer feel like the centre of everything. That psychological shift might be the most meaningful boundary of all. There is also another way astronomers think about the edge of the solar system, involving something called the heliosphere. This is the region around the sun within which its gravity dominates over the gravitational pull of the galaxy. The sun's heliosphere is enormous, extending perhaps a couple of light years in radius. Within this region, objects are more strongly influenced by the sun than by any other star. Interestingly, the nearest star system, Alpha Centauri, lies just over 4 light-years away, which means that the sun's gravitational sphere of influence extends a significant fraction of the distance to the nearest stars. This perspective changes how we think about the solar system's size. Instead of ending at the planets, or even at the heliosphere, it may extend deep into what we normally think of as interstellar space, blending gradually into the gravitational fields of neighbouring stars. Another subtle boundary involves comets. Long-period comets arriving from the Oort Cloud are influenced not only by the sun, but also by passing stars and the tidal forces of the Milky Way. Their orbits can be altered by events occurring light-years away. This means that the outermost parts of the solar system are not isolated, but are part of a dynamic interaction with the galaxy. The solar system, in that sense, is not a closed system. It exchanges material and energy with its surroundings. Comets can be ejected into interstellar space. Interstellar objects like the mysterious visitor, Oumuamua, can pass through the solar system, briefly becoming part of it before continuing on their journeys. These visitors remind us that the boundary between star systems is not a wall, but a region of transition where objects and influences overlap. There is also a temporal aspect to this boundary. Over billions of years, the sun moves through the Milky Way, orbiting the galactic centre and passing near other stars. These encounters can reshape the outer Oort Cloud, stripping away some objects and capturing others. The solar system's outermost regions are constantly evolving, shaped by events occurring far beyond the planets. So when we ask where the solar system ends, we're really asking several different questions at once. Where does the sun's gravity cease to dominate? Where does the solar wind give way to the interstellar medium? Where do objects remain bound to the sun, and where do they drift free? Each of these boundaries lies at a different distance, and each fades gradually rather than appearing abruptly. There is something quietly comforting about that idea. The solar system is not sharply separated from the rest of the universe. It is part of a continuum connected to the galaxy, influenced by distant stars, embedded in the broader structure of the Milky Way. If you were drifting far beyond the heliopause, looking back, the Sun would be one star among many, though brighter than most. The planets would be invisible, lost in the glare of that distant point of light. The solar system, which from Earth feels vast and complex, would appear small and quiet from that distance. And yet that small, quiet system contains everything we know, everything we have ever experienced, every story and memory and a moment of human history. That contrast between the vastness of space and the smallness of our home is one of the themes that runs through astronomy. It does not diminish our world. If anything, it makes it feel more precious, more remarkable, a tiny oasis of life in a universe of immense distances. Looking outward from the distant edge of our own solar system, it is natural to wonder how it compares to others. For a long time, that question was impossible to answer, because until the late 20th century, we did not know whether planets existed around other stars at all. Astronomers suspected they did, of course, but suspicion is different from evidence. The stars were too distant, the planets too faint, and the techniques needed to detect them had not yet been developed. Then, in the 1990s, something changed. The first confirmed discoveries of planets orbiting Sun-like stars began to appear. At first, there were only a few, and many of them were surprising. Some were enormous gas giants orbiting extremely close to their stars, much closer than Mercury is to the Sun. These so-called hot Jupiters challenged existing theories of planetary formation and forced astronomers to rethink how planetary systems might evolve. Since then, the number of known exoplanets has grown into the thousands. Space telescopes and ground-based observatories have revealed an astonishing variety of planetary systems, some familiar in structure, others completely unlike our own. And that brings us to an interesting question. When we ask how big the solar system really is, part of what we are really asking is whether our system is typical or unusual. Is it large compared to others? Is it small? Or does it fall somewhere in between? To begin answering that, it helps to think about what we mean by size in this context. There are several ways to measure the size of a planetary system. One is by looking at the distances of the planets from their star. Another is by considering the outermost regions of cometary clouds and debris disks. Yet another is by looking at the gravitational influence of the star, the region where it dominates over the pull of nearby stars. In our solar system, the planets extend out to Neptune at about 30 astronomical units. The Kuiper Belt reaches perhaps 50 astronomical units. The heliosphere extends beyond 100 astronomical units, and the Oort Cloud may stretch tens of thousands of astronomical units into space. That last number is particularly important. If the Oort Cloud exists as astronomers believe, then our solar system's gravitational domain extends a significant fraction of the distance to the nearest stars. But measuring the size of other planetary systems is much more difficult. Most exoplanets are detected indirectly, by observing the tiny wobble of a star caused by an orbiting planet, or by measuring the slight dimming that occurs when a planet passes in front of its star. These methods are most sensitive to planets that are close to their stars, which means that many distant planets remain undetected. As a result, our picture of other planetary systems is still incomplete. We may be seeing only their inner regions, not their full extent. Even so, some patterns have emerged. Many planetary systems appear to be more compact than our own. In some cases, multiple planets orbit within distances smaller than Mercury's orbit around the Sun. These systems can have several planets packed into a region that, in our solar system, contains only one. This might seem crowded, but it is simply a different arrangement. The planets in these systems are often smaller than Jupiter, and their orbits remain stable despite their proximity. There are also systems with giant planets orbiting far from their stars, and some with debris disks extending hundreds of astronomical units outward, suggesting the presence of distant reservoirs of material somewhat like our Kuiper Belt or Oort Cloud. One of the most interesting discoveries is that planetary systems often form in ways that differ from the neat, orderly picture we once imagined. Planets can migrate inward or outward over time, interacting gravitationally with one another and with the disk of gas and dust from which they formed. These migrations can lead to orbits that are highly elliptical or tilted, very different from the nearly circular, relatively flat orbits of the planets in our solar system. In that sense, our solar system appears to be somewhat orderly compared to many others. The planets follow nearly circular paths in roughly the same plane, and there are no giant planets extremely close to the Sun. That arrangement may have played a role in the long-term stability of Earth's climate and the development of life, but in terms of size alone, it is not yet clear whether our solar system is unusually large or simply typical. Some observed debris disks around other stars extend hundreds of astronomical units, suggesting that large outer regions may be common. On the other hand, many systems detected so far appear more compact, though that may be partly due to observational bias. Another way to think about this is to consider the distances between stars themselves. The nearest star system, Alpha Centauri, lies about 4.37 light-years away, which is roughly 275,000 astronomical units. If the outer edge of the Oort Cloud lies at around 100,000 astronomical units, then our solar system extends a significant fraction of the way toward the nearest star. That comparison highlights just how large our solar system really is, not just in planetary terms but in its full gravitational reach. It also reveals something else. The space between stars is not completely empty of structure. Each star may be surrounded by its own cloud of distant icy bodies, its own heliosphere or astrosphere, its own extended region of influence. These regions may overlap or interact over long timescales, creating a complex and dynamic environment on a galactic scale. So when we compare our solar system to others, we are really comparing regions that are often difficult to observe directly. We see the inner parts of other systems more clearly than their outer reaches, just as an observer from another star might see the inner planets of our solar system more easily than the distant Oort Cloud. There is also a philosophical aspect to this comparison. For centuries, people wondered whether our solar system was unique, whether the arrangement of planets and the presence of Earth were rare or common. The discovery of exoplanets has shown that planets are abundant. There may be billions of them in our galaxy alone. Some of these planets orbit within habitable zones, where temperatures might allow liquid water to exist. Others are gas giants, ice giants, or rocky worlds unlike any in our solar system. This diversity suggests that planetary systems come in many forms. Our solar system is one example among many, neither the largest nor the smallest, neither the most crowded nor the most sparse, but one variation in a vast range of possibilities. There is something quietly comforting about that realization. It reminds us that the processes that formed our world are part of a larger pattern, a pattern repeated across the galaxy, shaped by the same physical laws, the same interplay of gravity, motion, and time. And yet, even as we recognize that our solar system is one among many, it remains our home, the only planetary system we can explore in detail, the only one where we have sent spacecraft to multiple worlds and begun to map the distant frontiers. Thinking about other systems also helps put our own into perspective. The distances that feel enormous within the solar system are small compared to the distances between stars. Light takes hours to cross the planetary region, but years to travel from one star to another. In that sense, the solar system is both vast and small at the same time. Vast compared to our everyday experience, small compared to the galaxy. That dual perspective is part of what makes astronomy so fascinating. It constantly shifts our sense of scale, reminding us that size and distance are always relative to what we're comparing them with. By the time you've followed this journey from Earth outward, through the Moon's orbit, past the planets, across the Kuiper Belt, and into the distant regions where the Sun's influence fades, the idea of size begins to feel different than it did at the beginning. At first, the solar system may have seemed like a collection of worlds arranged in a tidy sequence. Now it begins to feel more like a vast landscape, a region of space so large that even light, moving faster than anything else in nature, needs hours to cross the planetary realm and years to reach its outermost gravitational boundaries. And yet, for all that vastness, this immense region is also home. Every human being who has ever lived has spent their entire life within a tiny fraction of this enormous system, on a small world orbiting an ordinary star. All of our history, all of our languages, every city and field and ocean, every memory and discovery has unfolded within a narrow band of space less than 1 astronomical unit from the Sun. That contrast can feel surprising at first. The solar system is unimaginably large, and yet our lives unfold within a space so small that, on a cosmic scale, it would be almost invisible. But there is another way to think about it, one that feels quieter and perhaps more reassuring. The fact that our lives unfold in a small region does not make them insignificant. It simply means that we are part of something larger, something that extends far beyond what we can see with our eyes alone. Consider for a moment how recently we began to understand the true scale of our surroundings. Only a few centuries ago, most people believed that the Earth was the centre of the universe, and that the stars were fixed lights embedded in a nearby sphere. The distances to the planets were unknown. The idea of other solar systems, other galaxies, or interstellar space lay far beyond imagination. Step by step, observation by observation, that picture changed. Telescopes revealed moons orbiting Jupiter, showing that not everything revolved around Earth. Measurements of planetary motion revealed the scale of the solar system. Spectroscopy revealed the composition of stars. Spacecraft carried instruments beyond the atmosphere, then beyond the moon, then beyond the planets. Each of these steps expanded our understanding, not by leaps, but gradually, patiently, one careful measurement at a time. There is something deeply human in that process. Curiosity leads to observation. Observation leads to understanding. And understanding leads to a new sense of perspective. That perspective does not diminish our world. Instead, it places it within a broader context, showing how remarkable it is that a small planet, orbiting at just the right distance from its star, could become a place where life emerged, evolved, and eventually began to ask questions about the universe itself. It is easy to overlook how extraordinary that is. When you think about the vastness of the solar system, it becomes clear that most of it is empty, cold, and silent. The planets are separated by enormous distances. The outer regions are dark and quiet, illuminated only faintly by a distant sun. The conditions that allow liquid water, breathable air, and comfortable temperatures exist in only a narrow region. And within that narrow region, on a small world with a thin atmosphere and a stable climate, life found a way to take hold. Over billions of years, simple organisms evolved into more complex forms. Forests spread across continents, oceans filled with living creatures. Eventually, a species appeared that could look up at the night sky and begin to wonder what lay beyond. That capacity for wonder is one of the most remarkable aspects of being human. It allows us to imagine distances far beyond our everyday experience, to measure the motions of distant worlds, and to understand the structure of a system that stretches tens of thousands of astronomical units into space. At the same time, it allows us to appreciate the smallness and fragility of our own world. Astronauts who have seen Earth from space often speak about the same realization. From orbit, the planet appears as a single, unified sphere, with no visible borders, no divisions, only clouds and oceans and land. The atmosphere, which feels vast from the ground, appears as a thin, delicate layer, barely visible against the darkness. That perspective, sometimes called the overview effect, can change how people think about their place in the world. It reminds us that the differences and conflicts that seem so important on the surface are small compared to the larger reality of our shared home. Thinking about the solar system can have a similar effect, but on a larger scale. It shows us that Earth is not the centre of everything, but one world among many, orbiting a star that is one among billions in a galaxy that is one among billions in the observable universe. And yet, even within that immense context, our lives still matter, because meaning is not measured in kilometres or astronomical units. It is measured in experiences, relationships, and the quiet moments of awareness that connect us to the world around us. There is also something calming about the steady, predictable motion of the solar system. The planets move along their orbits year after year, century after century, guided by gravity and inertia. The Earth turns day and night without fail. The moon circles the Earth. The seasons change in their familiar rhythm. These motions have been continuing for billions of years, long before humans appeared, and they will continue long after we are gone. There is a kind of quiet stability in that thought, a reminder that the universe operates on timescales far beyond our own. Sometimes, reflecting on those timescales can be surprisingly soothing. The worries and concerns of a single day, or even a single lifetime, are small compared to the slow, steady movements of planets and stars. That does not make them unimportant, but it places them in perspective. Another aspect of finding our place in the vastness is recognizing that exploration is an ongoing process. The solar system is not fully understood. There are still mysteries to solve, still regions to explore, still questions to answer. What lies in the distant Oort Cloud? How did the planets migrate in the early solar system? Are there undiscovered objects in the outer regions? Could there be life in the subsurface oceans of moons like Europa or Enceladus? These questions remain open, inviting future generations to continue the journey of discovery. And that journey does not require travelling billions of kilometres. It begins with curiosity, with the simple act of looking up at the sky and asking questions. Even tonight, wherever you are, the solar system surrounds you. The Earth is carrying you through space at tens of kilometres per second, orbiting the Sun, which in turn orbits the centre of the Milky Way. The stars you see are distant suns, each with its own history, perhaps with planets of their own. All of this is happening quietly, steadily, without any need for attention or acknowledgement. The universe does not rush. It unfolds at its own pace. There is something restful in that realization. The vastness of space is not something pressing or urgent. It does not demand anything from us. It simply exists, offering a sense of scale and perspective that can be both humbling and calming. When you think about the size of the solar system now, after tracing its structure from the inner planets to the distant cloud of comets, it may feel less like a number and more like a place. Not a place you could visit easily, but a place you belong to. A region of space shaped by the gravity of our star and the history of billions of years. And within that region, on a small world orbiting at just the right distance, you are here, listening, breathing, aware. That awareness, quiet and steady, is itself a kind of connection to the universe. Every atom in your body was formed in ancient stars long before the sun existed. The elements that make up the earth, the oceans, the air, and all living things were forged in stellar interiors and scattered across space by supernova explosions. In a very real sense, we are part of the universe becoming aware of itself. That thought does not need to feel grand or overwhelming. It can simply be a gentle reminder that we are connected to something larger, something that extends far beyond our everyday concerns. As the night deepens and the sky turns slowly overhead, the solar system continues its quiet motion. The planets follow their paths. The distant spacecraft drift farther outward. The sun shines steadily, as it has for billions of years. And here, on this small, warm world, there is time to rest, time to breathe, and time to let the vastness of space feel not intimidating but peaceful, like a wide, quiet landscape stretching beyond the horizon, always there, always steady, carrying us along.